The plan this afternoon is I swapped 2 days because it was making more sense to have the inert matter first day, active matter second day, third day collective effect, and this afternoon analysis of the movie of day 1, day 2. That was much more logical, so that's why I swapped today and tomorrow. Tomorrow it will be system biology. So this afternoon we're going to work on your movies. So I think the best at this stage is that, yeah, I also get rid of this. And we're going to work on the data that were acquired on day 1 and day 2. So we have the drive. So I'll be very short in the introduction so that you have the time to analyze the data, and then I'll go through your analysis flow. So we have the Google Drive, and I'm going to project so that I'm going to take random movies. Come close, come close. And so the menu of this afternoon until 4:30 is going to analyze your data, where in fact we have day 1 data that was particle motion. And you had 2 types of movie. You had 3 micrometer beats. Yeah. It's okay? Yeah. There were 3 micrometer beats. And there was 6 micrometer beats. And there were day 2 data, which was, I'm going to call them microorganism, right? To find a name. So it's going to be microorganism motion. And we had 2 types of, yes, there is a question here. No? There are 2 movie, 3 micrometer, 6 micrometer, SMH sample and KH sample, and to extract numbers out of them. So 2 hours will not be enough, definitely. But at least it will be a way to get started, to take your movie, convert them in the right way, integrate them into imagery, and then take data out of it. You have a question? No. So what I would like at the moment is that simply we look at the data as they are. We just comment them a little bit, and then you delve into the analysis so that we are ready to go. So unfortunately, all the data are not yet there. If you probably have internet, so then you will be able to put them. Is there any volunteer so that I project his or her movie? There is a question over there. Yeah, there is a question. You have a question? No? Okay. So I'm showing here day 1. Anyone is volunteering so that I show the movie, or it would be easier than, anyone? I click randomly? I'll click randomly. Okay, good. So I don't know which movie I'm going to open now, but let's try to open this one. You are in the room or you're not in the room? Okay. So this is a motion. Who is it? Who is the person? It's you. Great. Don't be shy. Shout, right, so that I see. So basically, this is your movie, right? So there is here a motion. The whole idea is that you're going to take the imagery software. You're going to track, maybe some of you have done it already. You're going to track the motion of this particle, and the idea will try to get a number out of it and to test the relation I was presenting during day 1. Okay? So this was which dimension for the sphere? 3 micrometer? Okay. This was the 3 micrometer bead. Okay, fair enough. And then I'm going to open also your sample for the day 2. So if you want to guide me, you are 3rd or 4th one? Number 4? Oh no, I'm in day 1, so I should go to day 2.
First one.
First one, okay. So you had one sample. Right. So you had a rich movie. Probably you had more movies, but you took the best one. So here you can see that it's obviously very different. There is no doubt about it. So you move here, so it's difficult. Yeah. So you were the group of the bubble. Oh, you're the group of the bubble, right? So basically here, well, you are moving still, but you can see here you have this one that was doing this type of thing. There was another one that were going very fast. Yes, you see here the rotary one, and yes, you have one that is moving here like this and then switching direction. In your movie, do you stabilize at some point? Okay, it's not good. Oh, this is the one that was rotating. Okay, good. So then you have this gigantic one, right? This was your hypothesis, I guess, or one of your hypotheses that somehow they were eating each other. That was the hypothesis that was run. And that was an interesting hypothesis. You see that this one is, okay, this one is moving like this. So directional motion that I talked about this morning is not an illusion. This is, they're really swimming. And basically, you see a variety of behavior. You see that one that was going like in this direction, right? So you had a very rich diversity of behavior with this pond water. I took a random example. I would like to invite you to put all your movies in it, right? I think I only have a couple of them here, but just please put them on the folder so that we have a shared, resources that will be extremely valuable. So, this being said, you see that there is an obvious difference between day 1 and day 2, okay? Now, before I go to the exercise of today, I want to show you it's a random internet place where you can have thousands of them, for which you will see which species you were having. So for the sake of the fun, I'll show them to you so that you see that you can have very good resolution, and it will make a link with what I was describing this morning with microtubular network. I mean, how do they swim actually? All of these objects are swimming, and they are all microtubular based, or the majority are microtubular based. So that you have a clear image, I'll show you this. Again, it could have been any other movie. That was, so I'll cut the sound. I mean, it's not indispensable, but basically, again, it's one movie where you see with a better resolution, this is paramecium. I think some of you had been seeing the paramecium. One of you was telling me, is it paramecium? So this we probably saw yesterday. You see the motion, you see the cilia on the side? These were the structures you saw probably. These were the structures I was showing earlier this morning with the microtubule 9+2. So with this microscopy, you see them nicely, but already yesterday you could see them. This is 2 paramecia. You see here the beating that is quite apparent on the side. For this, you need a better microscope, but essentially they were already present. You see also the very quick one this is still the paramecium, but all around you have the very quick one. And there is another part of the movie. Yes, Vorticella is very funny. So it has also some beating at the top. Again, microtubule, the same structure that I was showing to you this morning. So this is the core of the motion. And you see here all kinds of, flow that are promoted. And that's a way for the species to eat, actually. So you were wondering if they were eating each other. They are eating each other. They promote also a flow with this beating. You see the swirl that is happening here. So you get a sense somehow that this microtubular network organized with the dynein is allowing the system to beat like this, to eventually move, or to promote a flow and to eat. It is another species, Vorticella. I'm going to move forward so that you have another example. This one is also funny. You see the flow that is getting promoted in order to inject in their organism and to eat. actually. You see the inside of the, yes.
And what's the typical size of these Vorticella?
Vorticella, about-ish 1,000 micrometer. Yes, we're going to see multicellular organism here. I mean, we are really large in scale. The Volvox in particular that we will see in a second. And so on and so forth. Diatom are happening. I think there is another one that we saw yesterday, which I want to highlight, which is the algae. We didn't see much, I guess. I wanted to show you okay, this one we saw. Yeah, I think many of you saw it when I was going around because they look like, they have a chirality for sure. It's built in here. And there is, I'm sorry?
What was that?
This one, I want to make sure that I'm not saying something wrong. Apparently these are bacteria. I'm not sure about their name actually, but apparently they belong to the bacteria. I saw the name in another website actually. And then, well, this is a flatworm. I'm not sure we saw them yesterday. But the last one I wanted to show you was Volvox, because I think you saw them, many of you saw the Volvox. Amoeba, I don't think any one of you saw. And the last one is the Volvox I wanted to show because it's pretty nice actually. No, I don't think crustaceans you saw. Yes, the last one I would like to share is the Volvox, and then we are ready to go for the measurement. But basically, the point I'm trying to convey is that all of them are based on cilia flagella. And that allows them to make this type of thing, either to promote a flow or to eat, or either to promote force on the surrounding and to move forward. So I want to show the rotation of Volvox, because I think two groups saw the rotation of Volvox, and you will see it again. Yes, so there are many, many examples online, actually. Yes, so I'm really taking a random one. So this is now visible. I think you were 2 or 3 groups seeing it. Yes, it should. Right? So who saw these ones? No? Who saw this rotation? I mean, there were 2 groups who saw it. I remember. Nobody saw this rotation?
This big one?
Big one, yes.
Yes.
I think you saw it basically. So this is Volvox. This is like more 100 micrometer-ish. So it's multicellular organism promoting the rotation. Good. So the game of today actually is going to be like this, and this is a proposition for me to somehow allow you to move forward in the analysis of the motion. I suggest you keep your groups. You analyze your all the data that you've been producing, and by 4:30, basically, I would like that you follow the following track. For both of them, you're going to use ImageJ or Fiji to make a tracking of each quote-unquote particle. So with this, basically, you're going to have the center of mass of this bead of 3 micron, the bead of 6 micrometer, and the multiple species you were seeing moving. So the step number 1 is to acquire the trajectories. If you agree, I would like that you put your analysis on the same folder online, Google Drive. That would be also a way for me to follow what you are doing and potentially to help you at some point. So the first element is to basically take these movies, put them into Fiji, and then try to track the particles. Once this will be done, you are going to use these trajectories to make sense of this trajectory. And for this, there's going to be two strategies. I hope we'll manage to cover both strategies before 4:30. If not, you're invited to continue tonight or the day after. One of them is to plot the mean square displacement of the motion. Basically, you're going to take all the trajectories and you're going to analyze them in order to plot the MSE. An alternative one is going to plot something that is called the PDF, which is basically how long is the step at every time point. Basically, if I'm waiting 1 second, 2 seconds, 5 seconds, 10 seconds, what is the distribution of steps that I'm doing? The two measurements are not the same. They are taken from the same set of data, but they are not the same. Come close, close, close. There is, sit here. Yeah, second row. So in this case, it is the mean square displacement. Here is going to be the distribution function, basically, of each of the steps. And by the end of the day, hopefully, we're going to be able to compare the behavior of the passive particle and the behavior of the active living particle, only based on the trajectories. Okay? So that's basically the essence of what I would like to share this afternoon. Last but not least, and either we start by this or we finish by this, it's a bit as you wish. For this sample, I would like that you try to categorize the number of species you had. And so ideally, there should be an extra part for this one that is going to be list out organism. You can go on internet for that. There is, if you Google pond water species, you will have all the species that are present, and with your movies you can recognize them. And ideally, it would be good that you differentiate SMH, pond water, from KH, pond water. I understood that some of you live close to SMH and others live close to KH. Is it correct or not? No? Yes. So basically, that's a way also for you to know what's in your surrounding. Is there a way an objective way to differentiate between one or the other? That's the menu for this afternoon. It's okay? So please get started. I'll try to circulate among you to try to help you. Some of the elements I will discover with you, again, I'm discovering your movies, you acquired them yesterday afternoon. So is there any question? It's clear I'm summarizing for those who arrived late. The game of the afternoon is to put all your movies on the Google Drive, very well classified, extracting the movie as stable as possible. You don't change the scale, it's like stable. You see jiggling for day 1, you see direct in motion for day 2. You track the motion of day 1, of day 2, and the first, if you wish, step that I would like you to reach within possible an hour is the trajectories of the particles you will have been tracking. For this, please download Fiji, and there is one way that you can extract trajectories. Either you do by hand, if you are more comfortable with by hand, or you do it automatically with TrackMate or any other plugin that you would find relevant. Last element, I would like that you put unit. So the trajectories should be in micrometer, and the time should be in second. So I really would like that you have actual unit with actual velocity, actual diffusion constant. It's okay? Good luck. I'm here, I'm circulating. If you have problem, you shout, and I'm coming, okay? Do you want that we reorganize the room, or it's okay? Can you be the team together? You go with your partner? Yes. You go close to your partner, and you start analyzing the data. You should get started. At 4:30, we stop. So we have an hour and a half. Go close to your partner. Yeah, and please disconnect from internet and telephone. Otherwise, we won't manage to run the analysis. Yeah, So I want to see laptop and people analyzing data. Yeah.
You have to upload the video.
Yes, you have to upload the video. You might face a problem when you upload them because you need to, you need to change the format. They won't be uploaded directly usually. You need to change the format through TIFF. AVI or TIFF, but you need, there are different converters online and you can take any movies. Ideally, take your movie that is the most stable and please upload on the Google Drive also. It's okay? Yeah? No? You manage or? Okay, the more you ask questions, the better, but get started so that we can, you're going to face all kinds of problems and it's good that you say which one. Yes.
After you have this figure,
Yes.
so how to like select?
Select one, yes.
For it to track.
To track,
Like,
yes.
if I open TrackMate,
Yes.
so should I open TrackMate just after
Yes,
this, or
yes.
I should do some processing? On
You
this?
can do already TrackMate and give it a try with TrackMate, yes.
Okay, so if I go to tracking and
Yes,
TrackMate.
yes.
Okay, so first of all, I'm
Yes,
converting
that's right, into gray.
image.
Yeah, gray image.
Type, which 8-bit? 8-bit.
You can try with 8-bit.
8-bit.
Try whatever until, you know. Okay, now you are grayscale. A priori, the larger the bits, the better the resolution. Yeah.
So this, I'll increase the 32-bit.
You can, yeah.
Yeah, otherwise it will
And then TrackMate.
and close this and save. Image, duplicate. Okay. Image, type 32.
Yes,
So it's done.
yes,
Now, my question is like, if I open the TrackMate, there are a lot
yes.
of things it's saying which I'm not understanding. So, first
Maybe,
of all, it's saying
can I have a suggestion?
Yeah.
You work together in ICOM?
yeah.
I think it's better. Just go to and then yeah. So first of all, if you have a hard time uploading it, you're converting it, right? So you're converting it either to TIFF or to another format, and then you'll be able to upload. Preferentially, take your best movie, right? Don't take the movie that you are the less happy about. It's okay. It's okay. The computer is starting. Okay. It's okay.
So in what format we have to upload?
Yes. So you have to import or to open, and you open your best file, the one that you are the most happy about. Okay, let's say I don't know. I trust you. Maybe this is the best one. Yeah, sure. Yeah, you say okay. Yes. So you need to convert MP4 to TIFF, AVI or TIFF, and you can do this online or yeah. So first of all, if you have a hard time opening your file, you convert it to TIFF. TIFF file or... it's okay? Okay. It's okay? You managed to upload? You don't manage to upload, yeah. So I guess you all face the same problem, which is normal. So you need to convert, I need your attention here. So you need to convert your original files into TIFF, or AVI maybe works also. TIFF works. So you take your original file and you convert them to TIFF, and then you'll be able to open them on imaging, on Fiji.
So the video can be converted to TIFF.
That's right.
MP4 into TIFF.
And otherwise you will have a hard time opening it on Fiji. So you convert it to TIFF, and then you open it on TIFF. Yes. You work together first? Okay. Yes.
So we both were getting this problem.
Yes.
Like then we did
Yes.
something, I think.
Yes.
I don't know. So what is this error coming? It appears this image has one time point.
As one type of, yes, basically it has 300 slices, so meaning 300, but in fact it's not Z, it's T.
So Z is the position.
It will be position and T is time, so you want to swap.
We want, so it's not understanding which is what.
Yes, so you want to swap.
But isn't it normal that the slices will be of different times?
No, because your camera was acquiring at very time point, so you can swap. This is real time.
I'm asking that why is it not being able to recognize? Because mostly people will give time slices.
Yeah, but since you converted from your MP4 to TIFF, there can be some mistakes. So the answer would be yes. Okay, and then I'll let you work. It's okay? It's okay? You manage?
It's okay.
Yes?
Can this happen? So
Yeah.
we have this image
Yes.
as well as video.
Yes.
So in this software, what do we need to upload?
So yes, you need to upload the video, but you need to convert it to TIFF. TIFF, that's right. So maybe I'll write it for everyone so that do you manage? Yeah. Okay, I would like everyone to be on Fiji and disconnected from WhatsApp, because otherwise we'll have a hard time having the data, right? So. So you take the movie that you have and you convert the movie, the best movie that you have, either from 3 micrometer or for 6 micrometer or from the SMH OKH sample, one of both. Okay? You stand by the best one and you convert your file into TIFF files. You can do that online, and then you open the files of TIFF files with Fiji. All of you should be able to do that. It's simple, it's a conversion of file and then open it. Is it working now?
Yeah.
You manage? Okay. Is it okay? You managed to open? You managed to open?
There is internet. So
There is a problem of internet? Okay, you are, okay.
now I just got it.
Okay,
Just,
got it. So I'll let you go. Good. Yes. Who has opened already with Fiji? One group, two group? It's still in progress for them. So please tell me whenever you're done with the opening with Fiji, okay? Okay. So, you managed to upload your movies? Everyone? Did anyone has a problem to upload the movie at this stage? Or yeah,
I'm trying.
you're trying. Okay, it's okay. Good. So who did not manage yet to upload the movie? Can you raise your hand? The one who did not manage to upload the movie yet? Okay. I just want to crack this and then we move forward for the next step. Yeah.
The internet is open.
There is no internet? Okay. Anyone has problem of internet? Internet problem? Ah, okay. It's your personal internet or GNU? Okay, I had the problem earlier today. I thought I was alone, but you have your personal?
Personal also that there is also personal.
Personal
Is also
has been exhausted completely.
it has been exhausted. Yeah, it is pretty costly. Huh.
Also with personal data there is issue.
So it's a more significant issue. Okay. Okay. If it's becoming a problem, we'll find an alternative. Right. If internet issue persists, there is another way to run without internet, right? Okay. The one who have already uploaded the movie, now in principle, it would be ideal if you manage, if not, we can do it later on, that you give the time scale and then you give the spatial scale. The time scale, it is the time between each frame, right? And the space, you know it because it is given by the size of the particle 3 micrometer. So you know that your camera is composed of pixels. I don't know if you, and basically what you have is that if you have 3 micrometer, you'll be able to say 3 micrometer in my movie is equal to, I don't know, 20 pixels or 30 pixels. So that will be a way for you to say the spatial scale. It means that 1 pixel is going to be equal to X micrometer. And here it will mean that the time between frame is Y seconds. Okay? So I don't know when it is written. I mean, this you can figure out by measuring, right? You can calibrate. This, I'm not sure how you're going to find it because somehow you need to know what is the frame rate of your camera. But probably what I'm advising is that if you take movie that were 20 seconds long, you know that they take regularly pictures, and so you can divide the total length time scale of your acquisition divided by the number of frames, and you have the time frame between, you have the time between each frame. Okay? So I'll let you do this, and then we're going to run to TrackMate. This calibration part is important because at the end, what we want to know is to get numbers. We want to have diffusion constant. We want to have velocities. You know, we need these numbers. So there is an option on Fiji that is called calibrate. So in principle, with this, you can find. Yes? You managed to upload the movie? No? Because of internet problem?
No, sir, we have downloaded, but we are unable to find from where we have to upload it.
Okay. So did you upload? Did you converted it already? And it is on the download folder. Okay, so now you go to Fiji. And okay, Fiji is open already. Yeah, or you can maybe you go to search and you type Fiji. Yes, and then if you enter, no. So you have the folder with application directly. Folder with application on your PC.
Sorry?
There has to be a folder with all your applications. When you look for Word or for another application, there is not a centralized place where you have all your application. Yes. You know, whenever you have Word or whatever. Yes. Yeah. It's like when you install Word or any other, there should be, you know, there is a central place where all your applications are present. And if you click on it, you're going to be able to open. I don't know if you would look for Word or Excel or any or PPT. Sorry. Yes. You installed it already or not yet? Did you install Fiji already? You have? Okay. Could you help them installing Fiji?
अपने सिस्टम देखो ना तुम्हारा वो सिस्टम में जाके वहाँ देखो सिस्टम प्रॉपर्टी सेटिंग्स में ऑलरेडी इंस्टॉल कर दिया तो उसमें पे फोल्डर खुल रहा है जिसके अंदर बहुत सारे फोल्डर्स हैं अच्छा आप लोगों में कौन सा है
ये वो लैपटॉप की होगा 32 या 46
हाँ
64 बिट लोडिंग ना
यूजुअली क्या होता है 32 समटाइम्स एक्सेसिबल होता है नहीं होता है पर 64 जो है वो तुम्हारे पीसी टाइप से पता चलेगा
So yeah, probably it's not installed yet. That's okay. Yeah. So that would be the reason. So then they need to go to 32.
Huh?
They need to go to 32 to make it run.
I don't get
They need to get to 32 to install it. That's what you said?
no they are just compatibility of the system. There are two versions of the
Yes. Of Fiji.
first is the
Okay.
32 bit
Yes.
and the other is the 64 bit. Usually PCs and computer are compatible with 64 bit.
Okay, so that's
These are
why-
related to architecture of the hardware.
Yes. So you say they should upload.
It could be 64 and if it is a very new computer then it only compatible with the
Okay. It's a new computer? Okay. So that's the reason. Okay. Good. Thank you. Thank you so much. Right. You managed to open it? Okay. Okay. Yes. So first of all, you need to know it. So how many images do you have in your movie, and how long was it lasting?
So how do we know this?
So you know because whenever you were acquiring with your cell phone, you know the total time. It's written on your.
Yeah, okay.
So basically, and if you divide by the number of images, it will give you basically if you had a 30 seconds movie, 300 images.
Images.
You divide 30 seconds by 300, it means that you have one image every 0.1 second.
So the number hasn't have to be accurate.
Well, it's accurate what I told you.
Okay.
It's basically, you know, it's written that, I mean, you need a calibration. So I don't know how many images you have in your movie, but if it is
30 seconds, 300 images.
Yeah, when you open it, it should give you a given, it's 300, so, and it's 300, what was the time of acquisition total in your cell phone?
120 seconds.
I'm sorry?
1 minute 30 seconds.
So you need to divide, you need to convert 1 minute 30 seconds into seconds. So it's going to be,
Seconds.
yes. So that you know, yeah, it's been that time, frame 1 was time 0, frame 2 was 90 seconds. Well, in your case, you told me it's a minute and a half.
1 minute
You,
30 seconds.
so then
It's 90 seconds.
90 seconds. So you divide 300 seconds by 90 seconds. And then it tells you that, and you need to do the same exercise for the spatial scale. You need a ruler for time and for space.
Okay.
Okay? It's okay? It's clear? Okay. Okay. Do you manage to open? Little by little. Internet, okay, I'm sorry for this, but yeah. Is it okay for you? Is it okay for you? Can you... hello?
Hello.
Did you manage to upload?
Yeah, I'm opening it.
Okay. Yes. What do you say?
Sir, after uploading this,
Yes.
what to do next?
Okay. So what I was saying is that you need to calibrate. So meaning you need to know the time between frame, and you need to know the pixel size of your movie. So the time between frame, you have a way to know it, because if you know, maybe I'll explain to everyone, otherwise I will repeat 10 times. So I'm going to explain to everyone, I think it's best now, who has not opened the movie? Everyone opened the movie? No? Okay. Because of internet or because of something else? Okay, did you go to TIFF files and it's not opening? Okay, tough luck. Who used TIFF files to open? Okay, which converter did you use to have the TIFF files? Yes, M converter, and it was working? Okay, use M converter and go to TIFF file, and then you should be able to open your files. But the point number 0 is really to open the file. And so first go to TIFF file. Once this is done, you need to calibrate, basically. The first thing is to open it, and the next is to calibrate. Okay, maybe a question for everyone. Why am I insisting that you calibrate? Why is it essential to calibrate? Yes. Because at the end of the day, what do we want? We want to have a mean square displacement, which is going to be in micrometer squared per second or something, so we need the space and we need the time. And also, we absolutely need to measure a speed for the moving organism. So we need a space and we need time. It's okay? So now I need silence from everyone. Because I've been receiving many times the same question, and just I would like to explain it to everyone. Yes, 2 minutes of silence, if you agree.
Okay. Everybody.
So this first step, some of you have some issues, and probably they will be solved relatively soon if you go to M converter and you go to your original cell phone movie and you convert it to the TIFF file. The second point is to calibrate the space and calibrate the time, because we want to deduce diffusion constant to the mean square displacement, and we want to deduce also velocity of the microorganism. So for this, you need to calibrate. How to calibrate the time? I had the question here. So there is a simple way to go for calibrating the time. You have your movie, which is, let's say, 300 frames. When you open on Fiji, you're going to have 300 frames. If you know that 300 frames correspond to a movie of 30 seconds on your cell phone, what should you do to have the time between frames? You divide, right? It's simple, not difficult, right? It's time t0 will be t0, t1 will be 0.1 second, and so on and so forth. So you will have a calibration of the time. Then you need a calibration of the space. Each of your cell phone has a camera, which is a series of pixels. A camera is basically pixel A1, A2, A3, A4, and there is a given pixel size. You need space. How can you have the space? Yesterday, Pramod gave you 6 micrometer beads. I gave you 3 micrometer beads. So depending on your movie you start with, basically you know which bead you have. So you take the bead in focus, and you take the ruler that is on Fiji, and you trace the ruler. It's going to give you a given amount of pixels. So 3 micrometer would correspond to, I'm saying something random, 30 pixels. Then 1 pixel is equal to?
3 micrometer is 30 pixels.
Yes.
So 1 pixel is equal to divide.
Yes? Point? Yes. Yes. So 30
1
pixels.
micrometer is equal to 10 pixels.
That's right. So basically 1 pixel is going to give 0.3 pixels. Okay, so it's simple. It's a simple division. Once you have this, you'll be able to measure by the end of the session, when you have the trajectory, or this evening or tomorrow evening, you will have the mean square displacement of the passive particle and the active particle and the velocity. But start by calibrating your system. Whenever you make a measurement, you need to know the time and you need to know the space. Sounds good? Good. Good luck. Now you can talk as much as you want.
About calibration. The meaning of calibration is we need to have a first frame point. Yeah, maybe.
You need to know the time between each time point. You have the image number 1, image number 2, image number 3, 4, and so on. But you need to know the time between the frame.
Okay, the total time divided by the scaling factor.
Yeah, that's right. And this I cannot know it.
Yeah. That's different for each and every system.
Yes, that's right.
Whatever.
As you were saying that all the students sitting in one row
Yes.
might be difficult for you to go and
To
check.
go, yes,
So maybe you can just
Sure.
distribute a bit.
sure.
Yeah, in the groups, let's say 2 people are doing together. Let's say the groups can also go there, and then he can then go and check what are the things.
And
going
by
on.
one. Yeah, please go ahead.
Yeah, so you just distribute yourself. Like here is too much of cluster people. So maybe 2 people can go in that some side and so on.
Reprocessing.
You had the calibration, time and
The time part
Yes.
is done.
you are on the space.
Scale.
Yes.
Everybody is connected to Wi-Fi.
Yes, sir. Scale of like this is the beats.
Yes.
So how do I measure? This is the
This.
scale.
Yes. But you know how to do it. You use Fiji.
No, I haven't used this.
You haven't used this. Okay. Which software are you using usually?
I had a program of my own on MATLAB.
You can use MATLAB. Right? If you want to analyze the data on MATLAB, you're welcome to do so. It's your call. I mean, you do the way you want.
Try and do it.
You're trying to do it with Fiji or with, okay. Fiji, okay. So basically here, what you can draw is you select a 3 micrometer bead.
So this is one beat.
Okay, I trust you, I don't know, but
Yeah.
but
if
basically,
it
you zoom.
Zoom.
You zoom, yes. If you want to localize the bead nicely, if I were you, if you want to, yeah, you zoom like a lot.
So these are the beats.
Yes, that sounds good. So zoom dramatically. You go to the zoom option here, on the top, and you're going to zoom like maximally. You click on it, zoom, like you zoom. Yes.
Yeah.
So can you play the movie to make sure? Yes, probably this is the bit. This is the one. Probably. This is the bit.
Okay,
So no, this is not. You know, that's why it's good to take the pure movie, because the pure movie you will know that it is actually the bead. So once you have the bead like this, somehow you can stop the movie. You take a bead really in focus, and now you're going to trace a line with this tool here. And it's going, if you zoom dramatically the bead, like you zoom until, no, but you need to be really zooming. You zoom the bead. Could you zoom?
More zoom.
zoom. It's completely out of zoom now.
Yes.
One click. No, just click. One
Yeah,
click.
you click, and you try to find the bead back.
Okay.
So then you need to play the movie to be sure that you are still on the...
I can also pan or can I pan? Can I move to the other parts?
Yes. I'll let you play a bit, okay? Yeah, yes.
You think that
Yes. Calibration. Yes. So, yes. So basically you can convert to a grayscale and you have a way to convert at the top. If you go to process or to image,
You have to select.
no, you go at the top, type, and then you can convert to whatever you want. You see, you match image, type, and you go to 16-bit, you try again, yes. Okay. Just click OK to see if it accepts to do it. I'm not sure it did anything, so try another one. Try 8 bits, maybe. 8 bits will be the minimum that you can have. You are in grayscale already. So go to 8 bit. Okay, it's doing it. So now you're going to have the proper format. You'll be able to calibrate, and instead of having pixel, you're going to have micrometer, which we need. For the time, you take the movie total time, and you divide by the number of frames. That will give you the time between each frame. It's okay?
What happens next? Calibrated.
Yes.
Okay, so it's about 0.3 microns per pixel.
Yes.
So that's the size.
Yes. What's happened next is that you use TrackMate
Okay.
to track. If I were you, I would start by a simple. You take one beat, very clear, and you make the TrackMate to be able to track trajectories. And
Maybe this.
yes, and you run TrackMate, and I'll come later on.
Right.
Okay.
Thanks.
Yes.
Sir, like my video is 90 seconds.
Yes.
And the frames are 300.
Yes.
So that gives me 3.3 seconds.
Yes.
That means the distance between the two frames is 3.3 seconds.
So tell me again, the total duration of your movie was
90 seconds.
90 seconds. And you have how many movies? How many frames?
300.
So it's 90 divided by 300.
90 divided by 300.
So-
or 300 divided by 90. Because we want frames per second.
You want to know frame 1, what is the difference in time between frame 1 and frame 2? So it's going to be 90 seconds divided by 300.
Okay.
So it's going to give 0 point something.
Something. Yeah,
Okay?
right.
Because otherwise, you see what I mean. So you need to go this to know what was the time between each frame. Okay?
And once we find out that, then what?
You need to measure the pixel size.
Yes, that's what this is 1 beat, right?
You need to fill your bid, yes, if it is a bid. So that's
And
good.
here I have measured this
Yes.
much. Now what?
Then you have a way that is called calibrate. You go on calibrate, probably you found it already. Yes. And then you need to convert to 8-bit grayscale to do it. So you go back to image and you convert. Okay?
But this is like, this is uploaded a video, right?
Yes, but then you can convert. If you go to image, you may type at the top, you go to 8-bit.
And now I do
And then you can zoom, and then you can calibrate. It's okay? You manage? Yes. So you have a bid.
select this.
So you zoom. Maybe I'll say to everyone because zoom, and then you need to zoom. And then you calibrate, and to calibrate you need to convert to 8 bits. Okay? It's okay? Yeah, you take a bid, and then you will have a pixel size. So then you zoom. When I said zoom, I was serious. You take the movie again, and you see the zoom option on Fiji? Yes, that's right, exactly. Zoom. Okay, you see the pixel now? So basically, I want to know, whenever you have 3 pixel, whenever you have 3 micrometer, how many pixel does it correspond to? So for this, you take a line. You see the line option somewhere on Fiji? Yes, that's right. And then you will say, okay, this corresponds, and then you will, if you go to calibrate is going to give you the number. You can either measure or you may calibrate directly. Is what's below.
And like
if you want, or if you want, calibrate, yes. So you need to convert to 8 bits, and then you recover, okay?
Excuse me, sir.
Yes.
Sir, after I'm selecting calibrate, it is opening this thing.
Uh, say okay, we'll see what's happening. Maybe only zoom at the moment. Zoom with the camera, yes, that's right. And you have another way is you measure the length of this. If you measure here, you have the line here, and you click measure. It's going, yes, that's right. It's going to give you the number of pixels.
No, it's just giving this length. Not
Yes, the length is 10 pixels. If you zoom, you're going to see that you have 10 to the minus 10.5 pixel. Zoom. You see what I mean? Count the pixel, or maybe you have more. So go back.
So that means this 3 micrometers is 10 pixels.
This is wrong, so there is an error somewhere, but I don't localize it on the spot. Why it's written 10? If you zoom, let's see, how many pixels do you count here? You count it, and then it should correspond. Yes.
Yes, sir. So we've calibrated the scale.
Yes.
So this is nearly, if you measure it.
Try to zoom maximally.
This is it.
You can zoom more.
From in Fiji.
Yeah, in Fiji. Whenever you calibrate, try to zoom with there is an instrument that allows you to zoom, and that will make the calibration better. Yes, this is the one, yes. So zoom as much as possible. You manage? Yeah, you zoom like the bit gigantic, right?
Okay, so we got it. And anyway, we're
Yes.
trying to say that in case we
And then you have different ways to measure. Yeah, either you do the, yes.
We have measured.
We had already measured.
But this is 4? No, it's not 4.
No.
No.
The
This
one particle
which-
is 4.4 micrometer.
Oh, you
Other one
calibrated
is-
also.
Yes, we
Okay.
calibrated.
Okay, good. So you already made the conversion between pixel.
Yes, we had already
And
made that.
in time scales also.
So you're
our
all
movie
set.
was 2.5
Minutes?
long.
So it
So
means
0.5 because 300. We divided the
to have in
150
seconds. Okay.
divided by 300. It's like 0.5
5
seconds per frame.
per frame.
And this corresponds to the reality, meaning that if you double check, it's always good to double check calibration.
Yes.
If you multiply the number of frames,
Number of frames with the-
multiply with the time between
Should
frame,
come-
should come to
Okay,
the total
other-
time.
yeah, we've done it.
It's working. Okay.
So it's-
So now you know the XY, you know time. Now you're ready to track the particle.
Got it. Okay.
And once you have the tracking, you are halfway.
So we need to go now to TrackMate.
TrackMate, that's
Yes.
what I advise. If you want to do it by hand,
Yeah.
you can do it by hand. You know, where you click, as you wish. If you are geek,
Okay.
um,
Okay, got it.
I mean, it's your call. If you prefer to do it automatically by TrackMate, go. Either way will be good. At the end, we want to have the numbers. So whatever you do will be fine.
Time and XY, both of
Now that you are calibrating, you are safe.
Okay.
Because you will know that what you make is measured. The only thing is that you need to make sure that the movie of the moving microorganism will have the right scale. Because if you zoom with your
scale will
fingers,
Yeah. So we need
not the bit size.
got it.
Okay.
Okay.
And another one, sir, can we annotate this particle? Like,
Yes.
we can definitely measure this particle size.
Yes.
Because we had already calibrated it.
Yes.
But say, for example, we just want to annotate it. We can.
You can.
We can annotate using
Absolutely.
just the scale bar.
Yes.
But if we want to annotate both these particles.
You can change color. There is an option where you change color. So basically, you can track particle, go to the next time point, you click, and then everything will go. This will be the manual way of doing it. TrackMate should do it automatically.
So I think we first go to TrackMate and then check.
Yeah. If it's working, great. If it's not working, well,
We'll see.
we'll see.
Sure.
I'll take a random one. And then after that, you can go to TrackMate or to whatever you want. So tell me where I should go. Oh, 3 micrometer beads. MP4 again. Yeah, but I would like to have already, if you put the movie directly, it will save some time. Yeah. Somebody has it already? You got it?
So one is uploaded.
Okay, which one?
You have to refresh.
Okay, right. So put all your movies inside.
Last one.
That's one, great, thank you so much. So I'm going to take this one, I'm going to download it. Now it's right here. Yes, so it's going to download, and now I'm going to open it on Fiji. Here we go, this is Fiji. And I'm going to File, Open. So this is the one? Yeah, okay. So this is the preview, I'm going back here. I'm going to File, Open. I'm going to the right folder, Download, it's this one. I have 300, and 300 corresponds to
1.24 seconds.
1
1 minute 24 seconds.
so it's 84 seconds. So you agree with me that if it is 84 seconds, I need to divide 300 by 84 seconds, and then it will give me the time between frames. So now I have the calibration for time. Now, if I want to have the calibration, for space, I'm going to take the motion of a bead. So here I need to be sure I identify a bead. So I'm going to play the movie, and I need to be sure this looks like a bead here, right? So basically what I'm going to do now, because it's not moving, it doesn't have a directed motion, I'm going to take here the zoom, and I'm going to zoom a lot on this bead. So I know where it is now, but I used to see it. This is probably the bead. Yes, here we go. So the problem is that the image is not very crispy, but still I can see something. So I'm going to reduce the size. I'm going to zoom out. And then I'm zooming in again. I want to have it exactly centered. And now I'm going to stop the movie. And let's say that here I'm happy. This is the bead, right? And it means that now you see the pixel, right? And it means that if I take, for instance, a line, I know that 3 micrometer correspond to 1, 2, 3, 4, 5, 6, let's say, 7-ish pixel. So now I have the pixel size, which is going to be 7 pixels divided by 3 microns. So it takes me that 1 pixel equals something, okay? So with this, I'm going to have the spatial scale. Is it clear for everyone? Okay? I mean, you have a rigorous way to do it. Back on the envelope is just to do this, right? So you see at the top here, I can read the number of pixels. The length. Here it's 4 pixels, 5, 6, 7, 8, right? It's written at the top here. If you don't see it, you have another way to do that, which is you go here, and you have an option which is here, Analyze, Measure. And if you go to Measure, at the end, it's probably here, Perimeter. I need to double check, but probably the 7 is right here. Okay? Okay, it's another place where you can see it. But with this, you have a calibration, if you wish, of the pixel size. Be very cautious when you will be making your measurement in the pond water, because in the pond water, also you zoom with your finger. And when you zoom with your finger, you're going to change the pixel size. Okay? So you need to be cautious and to be sure that the calibration that you make with the bead is corrected accordingly, otherwise the scale will be wrong. You see what I'm saying? It's okay. So you have either you write on your notebook the time between frame is equal to this, the pixel size is equal to this, and you keep it forever, or you can enter it into the program so it makes the measurement automatically. It's the way you want. I mean, it doesn't matter too much. At the end of the day, you just need to be sure about space and you need to be sure about time. Absolutely sure. This is the first step number 0. Okay? Some of you wanted to go through calibrate. If you want to calibrate, you need to change to 8-bit. Otherwise, I think the Fiji was refusing to do it. So if you want to go to 8-bit, you go here to Fiji, and you make here type, and you change to 8-bit. And then if you go to 8-bit, there is an option here which is called calibrate, where in fact you can run all the calibration so that it will give you the scale. Whatever you say doesn't matter. At the end, what you want to know is space and time. Once this is done, the last step to do is to have the trajectories. Trajectories of passive particle and trajectory of active particle. And for this, you need to take the center of mass of each of the particles. 2 options, TrackMate, and I think now most of you are ready to go through TrackMate, and you're going to travel in TrackMate with all the pros and the cons. Alternative option, you click. So it's boring, because then you are in front, you click, next time point you click, next time point you click, next time point you click, but at the end you will have the trajectories. So try one of the 2, and then the rest is work. I mean, the rest is essentially tracking, 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 tracking. And by 4:30, I hope all of you will have tracking. It's okay? Is it better? You asked me to, is it better now? Good. So good luck. And I'm traveling around, okay? Good. Yes, I'm coming in a second. Yes, yes, I'm coming. Yeah. Is it okay? Yeah? If you have, yes, please. Somebody was calling me. Yes. Yes.
We know now the frame.
Yes.
We know now the frame rate and.
You know time. So now you're going to plug in. Or?
Huh?
Plug in.
You have to go to plugin.
And you go down, down, down. Down, 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 down. Yes, tracking. TrackMate. TrackMate. Okay. So many of you are having the problem that it asks you to swap Z and T. So then you say yes. That's the easiest way to go. Because Z is a space. So Z, you travel in Z. And here, each frame is not Z. Each frame is T, is a time. So you accept to swap Z and T, and then it will start processing the data. Yes.
It's right field, it's not segmented that well. So if I'm tracking it, it's not really tracking the beat, but it is tracking some regions of background that have higher intensity.
Yes.
So how do I segment that?
So yes, it's going to be a problem, and since it depends on the quality of the camera, it's going to be random. For some of you, it will be very good. For others, it will be less good. So this is dependent. If it fails, I invite you to track by hand. Track by hand. So you click, and then you have the next time point. You click, and you click, and you click, and you click. Yes, you make an area of that region, and then you extract this region of interest. And either you try to run TrackMate, or you click and you have the trajectory. Either way. Right, in 10 minutes, I'm going to TrackMate and tracking, but first try yourself. It's better that you feel where the problem is before, because otherwise, you know, there is no problem. Thank you very much. Thanks, thank you. Yes? Yes.
After analyzing this time scale and spatial, what we have to do here?
Yes?
Next step.
I cannot see, sorry. Oops, I'm sorry. Yes. Now you have to track. So this is the point. Either you take the whole image and you run TrackMate. So you have TrackMate on your... you install TrackMate on Imaging or not? So maybe you have a plugin option. You go to plugin and you go down, and then you're going to have TrackMate on Imaging. Yes. And then you go to TrackMate. If you go down, TrackMate. Tracking. Yeah, tracking, it was good. Yeah, no, you're right. Tracking, and then TrackMate. Yes. And then you start running. Everyone found TrackMate? Okay? So then you run TrackMate, and some of you have already faced problem because of the quality of the image. So run through this. You have a way to make your life a bit easier, is to extract out of the movie a very clear region. So that if you copy a region that is very clean, if you extract it, you can run TrackMate on this very clean region, and then that should give you a perfect tracking. Okay? It's okay. At which steps are you? Which step are you? Yeah. In which step you are?
We are uploading the files.
Okay.
And then again
You're going to calibrate.
Yeah.
Okay, sounds good. You were blocked with internet, or you were blocked with internet? Okay, sorry. Okay. Yeah, because of the internet, yes. Okay, that's how you learn. It's okay. You're okay? Yes.
Should I use the thresholding detector?
Yes, that's a good one, because then you will have a different... If you want to make your life easier, you select a region which is very clean.
Like with this one?
You have a tool, yes, you have a tool to select. You can make a square.
This one?
Or you make a square, and you select with the square. And then you select, and you can has the option to duplicate.
First I should do the beads and then some other thing.
I think it would make your life easier, unless you are very comfortable with it. Yeah. It's okay? At which steps you are?
Sir, actually,
My computer is not.
What do you say?
My computer is
Is
not that much compatible, so I will do those things in my Linux system. I'm just learning it.
okay. And your neighbor, how is he doing?
They are doing good.
They're doing good.
So
We are just trying to segment
Okay,
it.
so I'll let you run. Okay. It's processing. Yes.
I've done I've converted in depot and
Yes.
uploaded in image.
Yes.
Now and also calibrated
Yes.
this size.
Okay.
3 micron.
Hoping it's the bid.
Ah,
I'm not sure it's the bid
yeah,
here.
I've made it 2-3 times.
Okay, it's
coming
you sure
around.
it's okay, sure, okay. Now you want to track.
Yeah.
Yes. How to track?
Yeah.
Okay. So TrackMate is one way to go, or you do it manually. Manually, it means that you click time T1, click time T2, click time T3, etc. Either way, as you wish. You prefer automatized or you prefer to click? You want to click or you want automatized tracking? So go ahead. You go to plugin. And you go down to tools, to stacks, sorry. Okay, some of you, okay, so maybe I should show to everyone. You received the email by Manoj to install the plugin. There was an email that he sent to everyone. So maybe I'm going to show on the computer so that you. So I'm continuing where I was standing. Some of you are already pretty advanced. So probably you can see my screen now. So you have your movie, you uploaded your movie, you calibrated time, you calibrated space. Now you are ready to make a tracking. A tracking is going to be what? What is a tracking going to give you? What do you say? Yeah, it means what? What concretely speaking, what is a track? So basically it's going to be a file that is going to be x, y, t. So x1, y1, t1, x2, y2, t2, xn, yn, tn, okay? So the way to go it, I mean, I'm showing you an example that you can see here. Here I've been tracking a random particle, right? This is fake, but basically this is a track. I have time t1, t2, t3, t4, t5, t6. This is essentially what I'm asking at the moment, is that you track the passive particle of day 1 and you track the active particle of day 2. At this stage, this is the punchline by 20 minutes, okay? So either you do it by hand, and then you will have a trajectory of one particle, or you try to do it automatically. So the point is that the way I managed to do that was essentially here, I was going to plug in, and if you go down, you have an option which is called tracking here, at the bottom of tracking. All of you, you don't have it. That's why I wanted to show to everyone. And here, I advise that you use TrackMate, and you go through the option. Some of you have already done it, and you face difficulty because the image is not crispy enough. So then there is a trick I'm going to tell you in a moment. If you're not happy with TrackMate, you can use manual tracking, or you can use manual tracking with TrackMate. This is what I used right before. And with this, I was clicking time T1, time T2, time T3. So I'm showing you the example with manual tracking. Manual tracking is like this. So I click. This is what I did here, and I ended up with a file that was giving me x1, y1, t1. The other option that I invite you to do is to run on plugin, tracking, TrackMate, and get through all the instructions that they are asking for, which are right here. And in principle, you will have the plots automatically if you go to the second one. If you face difficulty, what you can do is to take a zone of interest, which is good. You take it like this. Let's say this zone is good. And here you ask to duplicate. So it's somewhere here. It's in the stack, I guess. Crop. And if you crop, you're going to have a new file. No, this was not the right one. There is one which is duplicate somewhere. I know that there was one in the stack, I guess. No, it's not right here. I think it's duplicate is one of these in the image, and then it's duplicate. You're right. Stacks, you're right. And it's below duplicate.
It's below stacks.
Below stacks.
Below stacks, hyperstacks, there's duplicate.
You got it?
Left side.
Left side.
The main panel.
Yeah, yeah.
Just above it.
Just above it. Yeah, duplicate, you're right. This is what I was looking for. Thank you. So it's duplicate stack. Yes. Now it's what I wanted. So I have a larger one. And then I have a movie of this guy, which is not very good, but at least it has the merit to be one. If you run the manual track on this one, in principle, it's going to give you X, Y, T. And if you have X, Y, T, you are almost there. Basically, you will have an automatized one. So you have an option. Either you click and you save X1, Y1, T1, or you isolate a particle that you like, and you isolate like this. Is it clear? Good luck. Yes. Yes.
Then we have to calibrate, right?
Yeah, it means that here you know it's 3 micron.
Right. So when we are calibrating, it shows calibrate.
Yes.
Analyze, calibrate. It is showing that calibrate requires an image.
Yes. So then you go back to image, and you convert to 8-bit. No, at the top? No, no, at the top. You go to type, and you convert to 8-bit. And then you can repeat what you did. Calibrate. And then you say, OK. And basically, I'm not sure it did it, but actually what you know is that if you wish, another way to go is you do it by hand. You know how many, you trace the line again. Yes, you need the line. Yes, you trace the line. Why isn't it happy? Okay. If I were you, I would clear. You know, you can clear. Yeah. Type, shift. You know what? Can you erase and reopen the file? Doesn't want. You close the file and reopen it. This will be the best. Yeah. If you wish, there is either the option where you calibrate and then all your unit will be in micrometer, or you measure the number of pixels and you have the 3 micrometer, and that gives you, and that will give you the size of the pixel. Either way.
So suppose we have 8 pixels.
Yes.
Then we have to divide by 3.
Which way is right?
Means
Is
we
it
have
8 over
to-
3 or is 3 over 8?
We have to convert pixel to micrometer.
That's correct.
So 1 micrometer is 10 pixel.
It depends on, if you wish, how many, what is the number of pixels for 3 micron?
Oh, it depends on the
Magnification. That's why you need, that's why we put beads, because if you were zooming in, we didn't have any ruler. You see the point? So now you zoom, and now you can measure with the line. Okay, now you see the pixel. So I mean, do with the line. You can use the tool. You can draw a line. There you can use a line. Don't be too generous. You know, because here you have a blur, right? So you see, you can make here measure. You go at the top, and you have an option which is image. No, if you wish, or process or analyze. Analyze, maybe you go up, analyze, measure. No, at the top. Or measure. Yes, yeah. So if you go to the right, it gives you 14 pixel lengths. It corresponds to realistic. If you want to have a doubt, go back to the original image, and you count the pixel.
This one.
Yes. If you go down, yes. Yeah, it seems to be realistic, no? So then, if 14 pixel is 3 micrometer, 1 pixel is
1 pixel is 3 by 14.
it's okay?
Yes.
So now you know time and you know scale. Now you need to have trajectories. Okay? How are you doing? You're okay? You're okay? Yeah.
This is the result that I got. I don't understand what does this mean.
What?
These are the results
Yes.
of the TrackMate.
TrackMate? Okay.
What does this signify?
What does it? Yes. At the TrackMate should be a list of points.
I
So,
don't understand the track.
you know what? Can you show one trajectories? Can you isolate one?
So you asked us to mark. Right?
Yes. Yeah. Maybe select one that you would like to track. Select one particle that you would like to track.
From here.
Yes.
For example, if
No. Can you show me one movie that you like?
okay, the entire movie.
You can run this movie, but if you can zoom in a region that you like. Yes. Okay, so can you run the movie? Yes. So select one particle. Your image is very nice, by the way.
Yes. Thank you so much.
So take one zone. You take one zone. Yes. So this one is not moving. Take one that is moving. That will be more fun.
Okay.
Select the one that you
Most of the
want.
particles are following the same motion.
Yeah, but this one is a particle. Why don't you select this one? No? Zoom on it by taking the zoom option at the top right. You see where the zoom is?
No, so,
Here.
okay.
No, here. Right here. Yes. And you zoom here. Yes. Zoom. Ah, too much. Go back. Yes. And then you make a square around the particle. This one. The small one.
This
This one.
just
Just this one, yes.
Okay.
And now you're going to say duplicate. You go back. You go to image, and you make duplicate. You say okay. Duplicate. Okay. Now you have only. Okay. Play the movie. I think you didn't take all the slides. Duplicate again. Return to duplicate. Image. Duplicate. It's not a movie. So go back to image. Yes. There is something wrong. Go back to down, duplicate again. What's going on here? Yes. So yes, yes. So return to duplicate. Yes, duplicate stack. No, you should click on stack. Okay. Duplicate stack. Duplicate stack. Now you're going to have the 300 images. Okay. And now you can track. Okay. It's okay. I think almost all of you are in the right track, right? So basically, you need to have X1, Y1, T1. Yes. Yes. I have 2 ears, but 1 brain. So, yes.
They are asking same.
Maybe it is the same question, yes.
Yeah,
You can join? Yes, okay. Or, I mean, yeah.
Actually, I just installed this Fiji.
You are in San Fiji?
And just upload the file.
Yes.
And just calibrate the picture.
Yes.
So my question is now how I should calibrate the time.
To calibrate the time, it's your notebook.
How I have to insert the time.
Yes.
Interval.
I'll tell you, if you want to make it the easy way, you write on your notebook. Because at the end of the day, you're going to have X, Y, T. So if you have X, Y, T, you will convert delta T by real time. If you know that difference between 2 time frame was 0.1 second, if you have 10 time frame, it's 0.1 times 10, it's 1 second.
That thing I have done.
Yes.
I got the interval between two pictures and
Yeah.
then 0.08 seconds.
That's right. You can run everything without calibrating automatically. That will be fine. You don't care. At the end of the day, what you want is diffusion constant of velocity, right? So, yeah.
Okay. We tracking the one particle in 20 frames.
Yes. Yeah, very good.
So next what we have to do?
Yes, exactly. That's what you have to do.
What?
To have the file XYT.
So how we selected this position?
So either you go to TrackMate,
GBI in the
TrackMate, or you click and you click one after the other one, and you're going to have an XY, Y1, T1 frame.
We have to
Click in the center. Maybe I'll show to everyone. I think you are all on the frame. It's okay? I mean, you managed to have trajectories or not yet? You are on the way? Okay. So there are different ways to get trajectories.
So you need the length of one pixel, right? That's what you're putting in. That's it. So now go to add. I want to track this one. Where do you think it's the same? Keep it to the side. This is head to where do you think it's the same? That's all. Okay, then you internal. Yeah, just do it.
Right. So basically, the next bit consists of extracting some tracking. So I'm going to close some files so that you see where I stand. Don't save. Don't save. Tracking, tracking, tracking. Right. So I'm showing you one of the tracking. There are many, many ways to do it differently. But at the end of the day, what we need to have is x1, y1, t1, and a list of x1, t1, y1 for 6 micrometers, 3 micrometers, and all the particles you were having. So I'll show you one way to go. There are hundreds of ways to do it. So I'm going back to Fiji. I'm taking a random movie. I mean, it could have been another movie. And this is the duplicate option. That's actually, so this is, I'm taking this zone. It could have been another one, but let's say I'm taking this one. Now I'm going to go to image and then duplicate, as was said before. I duplicate the stack 1 to 300. I'm zooming. Now I can see the pixel. I have calibrated in time. I have calibrated in space. And now what I want to track is the center of mass. So the point is that I'm going to track. So there are different ways to do it. One way to do it is plug in. Again, going to tracking, and then making, so there are different ones here. Either you go to manual tracking with TrackMate, or mtrack2, or TrackMate, either one, whichever you prefer, you can run with it. So let's say I'm using this one. So I'm going to track the particle each time. So this is time, this is a zoom at the moment. I'm going to go to next. I can eventually select some time point, and then I'm going to next. And then, if I'm not mistaken, at some moment, I should be able to track. I took the wrong one, I guess. I took the wrong one. So I'm going backward. This is the tracking. This is the movie. I'm going back to plugin. It is on tracking, and then there is a manual tracking option, which I had just made a second ago. Yes, it's this one. So it's going to be at track. So I'm taking the bead here, I'm clicking. It gives me the position number 1. Then I'm going to the next time point. Let's say 10 times after, I'm clicking on the second one. I'm going to the third one. I'm clicking on the center of mass. I'm going to the next one. I'm clicking to the center of mass, and so on. And you see that on the right-hand side, I have a list of X, Y, and slice number, which is essentially the X1, Y1, T1 I was looking for. So I'm doing it the lazy way. I mean lazy. I'm doing it the easy way, basically, where I'm clicking, clicking, clicking. And at the end of the day, when I'm done, I can make end track. And if I end track, somehow, I'm going to have the trajectory that is here. I can go then to your favorite way of analyzing the data. It can be Excel, it can be Python, MATLAB, whatever you want. And with this X, Y, T, in principle, you are ready to analyze 3 micrometer bead, 6 micrometer bead, and your organism. It's okay? So I'm going to give the talk at 5:15, so I need a pause before. I think you need a pause also. I think we all need a pause. Can we say that we run 10 more minutes? Okay? and you write, you try to have one trajectory, okay? Not more, but one trajectory. And I invite you to continue working tonight, tomorrow, right? Whatever, right? Days, nights, right? Until you get trajectories. But at the end of the day, if you want to go from raw data of Monday and Tuesday to diffusion constant and velocity measurement, you have to go through the step that we did this afternoon. You have to. It's calibration, upload with the right format, calibration, XYT, and then work on the data, okay? So I'll let you run for trajectory and then we make a pause, okay? Yes.
Basically, I just took we took a small ROI from out of the entire image. This is an overlay of the different tracks. So it's not very segmented very well, but
it's very good. It's very good. It's excellent.
So we got these information. So at each point we have the X and Y, right?
Perfect.
So taking the first X and Y as the origin.
Yes.
And we just have to calculate the distance.
That's right. And now you have the velocity of your microorganism.
Yes, so that will be like multiple displacements from the origin for each track of time.
Absolutely.
And we just plot that.
Can you plot that? Yes, plot that. Perfect. Okay, there is one group who has it. Other group. Yes, one group has the tracking with the velocity and so on. Yes. Perfect. Other group, next group, who has it? You have either diffusion of particle or velocity of bacteria. You have it? I mean, but you are an expert already.
Yeah, we have the XY. So
Yes, just have the XY.
XY, you have T?
T
Yes,
is
it's
the frames.
Okay, can you plot?
Yes.
You plot.
Doing in the
Okay,
process.
it's okay?
In the process.
In the process. Okay. You're okay?
Battery low, sir, because of this laptop battery is down.
Battery down, okay. And your neighbor, you're okay? Laptop is down also? What did you say?
Battery finished.
Battery finished? You don't want, there is no power supply?
There's no power supply.
Sorry, okay. You managed to reach, you're doing okay, I'll let you run. You are on which step?
We are doing on the browser. Coordinates. We have to click on the
Okay? How are you doing?
Sir, we are close.
You're close, okay, I'll let you work. You have trajectories? You're in the process of having trajectories? Still, okay, I'll let you work, no problem.
Now you can select the region of interest. If it's a whole image,
You can make a square and then duplicate. Yeah, and then you duplicate all stack. So do you have all the, so you take a square and then you can image and duplicate.
What calibration does? Like,
Yes?
How to calibrate? Do we use this thing or
So you can do it by hand if you want.
we just try the number?
Yeah, you take the line, you take the line, you know the line option at the top, and you go from here to here, and you see at the top, behind you, just behind, yes. Can you do the line again? You can, yes, that's right. Yeah, you take the line. You see you have 6.87 pixel. So you know that 3 micrometer corresponds to,
6.8.
so it means that every pixel corresponds to
2.17.
each pixel correspond to 2 point. Yes. Okay. So basically, yeah,
So we
it gives you the calibration.
So we
Okay?
use them at the last only whenever we'll get the number.
Basically, it gives you that whenever you will have an XY position, you'll be able, whenever you have a difference in pixel, to convert it into micrometer. And for the time scale, you know the time between each frame.
Is there any particular option where we have to put that particular value
For tracking?
time scale?
Time scale, I'll tell you, it's a bit your call. Either you take everything in pixel and frame, and at the end you convert. I think that's the easiest way to go, because then you don't have to care about the software. You see what I mean? If I were you, I would take distance in pixel, time frame number, and since you know the conversion, after that you'll be able to convert. You see the point? You're going to have a trajectory. X1, Y1, T1. X2, Y2, T2. X3, Y3, T3. Right? Then you're going to make the difference between two X, and you will know the delta T. Then the conversion will be your calibration. Is it okay? Okay. It's okay? In progress? How do you track? You go to plugin. Yeah, that's good. You're doing it. I think you are tracking now, no? No, now you are calibrating, I guess? Yes. So you go to plugin. You go to track. Manual tracking, I guess. And then you say yes. And you add a trajectory. You click. You add track.
This track is already being followed.
Yes. So basically, you end track, and you make a new track, add track, and then you go to the movie, and you track.
Where is the movie?
It's behind you. Yes. So you need to track.
We have to keep on adding 1, 2, 3, 4, 5, 6.
This is the patient way. You click, you click, you click. Okay? Yes. It's okay? Okay? I'm sorry. I just need to pass. Sorry. Yes. Yes, you have X, Y, Y, T. Good. Wait, can I see the movie? Original movie? Yes? Okay, that sounds very good. So you have tracked, and can you plot the trajectory? Can you plot?
We didn't plot it, just get the data.
Okay, very good. Now can you plot? You can plot what? Python? You plot, yeah. You coordinate, yes. So basically you can plot X as a function of time, Y as a function of time.
Okay, the data we get,
Yes.
and we can plot using origin or something else.
Whatever you want. This is, yes. Do you use origin usually?
Yes.
So use origin. Or Python or MATLAB or whatever you want. Okay? Basically, once you have the trajectory, 90% is done. The rest will be the right-hand side, which we won't have time to do. But basically, once you have the trajectory, you can work on the trajectory and extract the parameter. But you can plot, plot with origin. Go ahead. Yes.
We've got here the value of T.
D? Oh.
36.8.
In which unit?
Okay, the unit should be.
You need to check your unit. Because ideally you want to have micrometer squared per second. Yeah. It's okay?
Something.
Great.
I don't know.
Okay, good. So it's linear. What were you? Okay, what was the original movie? It was.
I have less data points here. I have only 98 data points.
It seems very linear, no? Which you must like.
This is the particle diffusion one.
Okay, that was my question. So it's a diffusion one. Can you show me the movie? Okay, it's on the. Okay. You're okay? Yes. 1 minute, 1 second, and then I'm coming. Maybe to wrap up, at some point, I'll ask a couple of you to go to the board and to show what you had. I mean, I think you're getting there. It's good. Yeah. Yes.
So this is the real one. And this red one is the.
I think I tried.
This one? Okay, very good. Okay, good. Yeah. And you end up with.
So this is the one we got.
Yes, sounds good.
This is the linear fit.
Fit, okay, and you obtain which velocity?
But this is the values of the data was in pixels.
Okay, and you need to convert it into.
I didn't do anything. I just ran it.
Okay, right.
Okay, I'll do it now.
Now, okay,
So
convert
this
and
is like
see.
in units.
Yes, basically you should end up with a number now. Good. Right. I think it's very good because you are getting. You're getting there. I mean, there is diffusion constant obtained here, velocity obtained there. Put all your data on the Google Drive, right? All of them put on the Google Drive. Put everything, right? Maximally put everything. Yes. I have 2 calls. I can take one at a time.
It's
yes.
in micrometers square per second. Again.
38 micrometers squared per second.
36 micrometers square per second.
For a particle or for a microorganism?
For the particle.
3 micron. Let's compare with them. Yes. Yes. What is the next step? Yes. So ideally, if you have time, you should measure the mean square displacement. This is its value. It's x of t minus x absolute squared average. And you plot them as a function of time. What you are most comfortable with? I don't know. You code? Yes. So you code. Yes. Yes.
With the manual tracking,
Yes.
you have some points.
Yes. That's frustrating because you know it's.
Like there would be an average.
Yeah. The problem is that you need to have much more. But at least if you start by 1, it's a good start. Okay.
So, but then if instead of manual tracking, you use the TrackMan.
That would be.
The CSV file of all the.
Yes, as long as the segmentation is good. If the segmentation is bad, you will get numbers which are meaningless. So you need to be sure that the quality of the segmentation is of good quality.
That TrackMan, it will give me something, some different kind of figure.
Corresponding to something true or totally arbitrary.
Because some figures were completely arbitrary.
Yeah, tough life. Yes, then you're in trouble. So basically you need either to circle out and to duplicate, or you go to a movie, everyone will share their movie. So you select a movie that you want and you make the analysis. Share your movie. Everyone share your movie. Make it open. Yes.
We have the float of like this one.
It is the particle?
Yeah.
That was flowing or that was diffusing? Okay, not bad. Not bad. It is the beads or it is the... Okay.
It is the day first floor.
The first day, okay. I think there is a bead flow, but you know better than me. Probably all your beads were doing this.
Yes.
Yeah. So it means that there was a flow in your sample. So your measurement is biased by the fact that it was flowing. But that's life, right? Yeah. So when you plot this as a function of time, what does it give you? Yes. So
We did 90.
in which unit? What is your unit?
Micrometer per second.
90 micrometer per second. Wow. It's pretty quick. 90, there is a, well, it's too quick. You know, you see 90 micrometer per second, it's very quick. And I mean, yeah. It's okay. I think it's starting to work. This is good. This is very good. I mean, you see the difficulty of extracting numbers, right? Acquiring movie is easy. Taking numbers, it's another complexity. Yes.
No, that's the first one. It's not the only. It's the first one.
So they've got a value 0.3 something, but they've not got the units.
Unit, okay. So maybe the last step, and I really would like to make a pause before actually, is so some of you actually, you asked me what to plot. So I was suggesting that you plot x as a function of time or y as a function of time. If you want to be rigorous, I advise two methods to extract the trajectory. One method, the one that I recommend, is x of t minus x0 absolute average squared as a function of time. This is the mean square displacement. That's basically used throughout the literature and throughout the world to measure trajectories or characterize trajectories. So that's the canonical way to do it. I think some of you wanted to program it. You're welcome to program or to code it. If you plot this as a function of time, if you have a diffusion, it should give you something linear. But you have what you have, right? And one of the problems in this acquisition is that some of you had a flow. So the particle was moving like this, and it was passive. And as we saw, it cannot have a flow. So basically, whenever you analyze the data, be very cautious to start with data which are extremely clean. At some point, there should be no bias. Everything should be absolutely clean. When you are sure about this, you calibrate. Once you're sure about your calibration, you carefully analyze one track, then you plot, and when you are satisfied and convinced that all the numbers are right, you go to the second one, and to the third one, and then to the number 100. But go very, very slowly at each step, okay? So we need to stop very soon, because otherwise we'll be in trouble. Who got diffusion constant? Which number? What did you get for diffusion constant? 0. So 10 to the minus 3 micrometers squared per second. 0.024. And you obtained?
Sir, we've got the mean square displacement. That is 36.1 micrometers squared per second.
So mean square displacement is a functional dependency. So when you plot that, if your movie was not biased, so basically if your movie was a particle passive moving like this, if you plot the mean square displacement, you should have something that is linear as a function of time. And the slope is equal to 2D. That's basically, if you plot your tracking, that it should happen. Now the problem is that if you have a particle that was moving directionally, because you were taking your sample tilted, it will be biased, which is not, what you want. So basically, you need to be cautious in the selected zone that you are taking, that you are tracking, okay? Who was tracking with TrackMate and obtained nice trajectories? Can you show, and then we close? You want to come you come on the right-hand side and you show to everyone? So there is one group who was tracking with TrackMate and successfully, so I think it's good that. You can go here and you can project. You can put it on top, I guess. So please put all your file and folder on the Google Drive again, because then you can compare, you can check. I'm going to switch on the light. So you're going to see that either you do it by tracking by hand, which is laborious, it's difficult, and so on. If you do it with TrackMate, but if your image is very clean.
So that D is diffusion constant.
That's right.
So we've actually found the D.
Okay.
Manually.
So,
36.1.
but
not matching with it.
All right. So we need to discuss. Yes, it become green, so it's working or not? I see something here. It's working. Okay. Good. So you want to describe it? Maybe you need to switch off the light. Yes. The projector is on, I guess. Now there is light. And now it should project. Ah. So you want to explain what you did so that everybody benefits?
Since there were a lot of particles in our video, I decided to take a small ROI from it, which basically any ROI, I think it was somewhere around this. I just duplicated all of the stacks in that ROI, got this smaller region which has all the stack information. Yeah, the beads and bead moving. Next, the idea is to, so I tried using this smaller RY and tried tracking all the particles, but as you can see in the smaller image, what the way TrackMate was tracking the particles was that it was looking for local maxima. Since this was a bright field image and the beads are not necessarily the only particles that have. Yeah, so since this TrackMate looks for local maxima, the beads were not the only regions in the image that had higher intensity. Sometimes the halo around the beads had higher intensity, sometimes even the background. So without any thresholding, without differentiating between background and foreground, it detected a lot of spots, which was obviously incorrect. So using the same image, I just adjusted the threshold such that now I ended up with this. You can just try different algorithms that are already there. You can even begin with default thresholding and just manually tweak the minimum and maximum intensities, these two bars, and arrive at such a thresholding such that now when I play this movie, I see that even while the beads are moving, I can more or less track my beads reliably. Although it's not great thresholding, but at least it's the beads that are getting tracked. So I just applied the thresholding from here, made the image into a binary. From process, you can go to binary, make it into a binary, and there is another option called fill holes. So wherever the thresholding was able to identify the entire boundary of the drop on the bead, it would fill the whatever blank space it was not able to detect inside. It would treat it as a complete object. As you can see, some of these thresholded have this hole in the center, but others do not. Wherever the boundary is complete, it just treats the entire thing as an object, just for better segmentation, nothing else. And since once I had segmented this object, all the beads, then I went to TrackMate and I just went ahead with all the options were there. And in the end, there'll be, if you just go next. So I just had to decide what the size of these beads that I'm tracking would be. So although the beads are 3 micron, but since these images are not very focused, they have a halo around it. So I took 5 micron so that I can still track my beads. And in the end, if you overlay the tracks that you'll get for each of your beads with the image, with the segmented image, this is something that you would arrive at. So the purple lines around the objects show that they are actually tracking the bead, and the overlay lines on top of the image are the ones that show the tracks for each of the beads. Some of the beads are not tracked because there is one quality threshold parameter which when I set it to 1 gave me better thresholding. It would be an underestimation,
yes,
but still a better estimation of the.
So congrats, tracks. This is very good. I mean, you saw basically how it can be automatized and all the steps you made, thresholding, filling the holes as necessary. This is really, really great. Now I have one comment. First of all, congrats. This is all great. The main criticism that I have, you probably guess which one it is. The original sample that you selected has a drift.
Yeah, the ROI it will.
So it means that because you start with a drift, you're going to end up with everything is great, right? But you're going to end up with a trajectory which will be all biased by the fact that there was an overall drift in your sample.
Right.
So you don't have a diffusion. What you're going to have is a directed motion, which is, as we discussed, impossible for a passive particle.
That is true. All of our movies, unfortunately, have some amount of drift or the.
It's as rip. So again, thank you so much. Yeah. What I'm advising is that please, I'm repeating, put all your movies on the Google Drive. Some of your movies were perfect without any drift. So then, in principle, you are ready to plot trajectories with pure passive particle, trajectories of active particles, and I would like that you share with me before Friday morning your results. Okay? Good. Short pause. and then we are back to research talk. So the subtitle is Broken Symmetry, which justified the title I was giving, and the nature of the hierarchical structure of science. This is 1972. It's a while ago, but I think it's still very relevant. He writes, by symmetry, we mean the existence of different viewpoints from which the system appears the same. It is only slightly overstating the case to say that physics is the study of symmetry. So I'm looking at particle physicists. I guess you will agree with this, that somehow symmetry argument is the driving force for the majority of the physicists, whichever field they're coming from. It allows you to write energies with symmetry argument, to neglect some term, to add some term. So it's a very powerful way of treating any question whatsoever. And Anderson proceeds to say next, and I like very much this paragraph. He says like this: it seems to me that one may array the science roughly linearly in a hierarchy. According to the idea, the elementary entities of science X obey the laws of science Y. So he's trying to be provocative, and he succeeded. I mean, this article promoted many reactions, actually. He says that, okay, let's try elementary entities of solid states or many-body physics obey the laws of elementary particle. The elementary entities of chemistry obey the laws of many-body physics, and so on and so forth. The elementary science laws of science, molecular biology, obey the laws of chemistry. And then comes the point that I'm going to reach. The elementary of science, cell biology, obey the laws of molecular biology. So basically, there is a kind of hierarchy of X and Y, and he proceeds to weigh all the rest. This is a caricature, but it explains somehow the idea he's trying to defend. And then comes his point: but this hierarchy does not imply that science X is just applied Y. Somehow, it means, in the context of biology, that summarizing by saying that cell biology, actually, is going to be essentially elementary entities of cell biology obey the laws of molecular biology is wrong. It's an extreme, and I think more expert than me on other fields could play the same game. And then he says, at each stage, entirely new laws, concepts, and generalizations are necessary, requiring inspiration and creativity to just as great a degree as in the previous one. Meaning that the change of scale, when you go from nanometer for the molecular biology up to the cell scale, which is 10 micrometer, as we discussed heavily since Monday, requires inspiration, new concepts, new physics, new way of thinking. So this is from this that we're starting with the rules that we know from physics in other fields. Basically, it's a way of saying a change in scale drives a new type of treatment. So this is the motivation. And for those of you who are not trained in physics, are trained in other fields, a very intuitive manner to see that, and I will show that now, it's this movie, where you see a herd, essentially, and an ensemble of, you see a collective motion here, which is very nicely seen when you see it from the top. But indeed, what you see is that one animal is going to be influenced by the alignment of the neighboring animal. And so, as a whole, the collection is going to behave in a given way, which is not the individual behavior between neighboring animals. It's going to be a collective effect, a real collective effect, and you're going to have a crowd effect that is going to be extremely reproducible. You have some lines here. You have some boundary conditions which are set by the dog that are at the back. Consider everything that I'm going to say now along this spirit somehow. When you change scale, you have to consider the individual unit, but also the interaction between the neighboring object, and as a whole, they have a new behavior. And this is around this ensemble behavior that I will talk about, during this presentation, right? So it turns around the concept of more is different from understand, but stated differently, it is really this image that I'm trying to convey. Collective effects are different than the individual behavior. I know it's obvious for the physicist because we learn that whenever we make our studies, but I think conceptually it's not easy because it means that a change in scale requires new way of thinking, and this is basically the message of Anderson. So I want to highlight maybe one paper about active matter, which is basically what's happening inside the cell. It's a review of hydrodynamics of active matter. Christina Marchetti, one of the authors. In India, you have very active and prominent original activity, theoretical and experimental in this field throughout the country. And it's a review of modern physics. The way they present it, which is extremely inspiring, is that whatever scale you are, active matter is going to trigger this type of collective effect. So basically, you don't care about the scale, you're going to have this type of collective effect. And interestingly, even though the scale at which I will be describing everything that I'll be talking about, which is low Reynolds number, there is no inertia, so it's basically a viscous regime. Even though we change scale, the physics of active matter will remain the same. So this being said, now I'm ready to go for the stories. Punchline, more is different is what we're trying to see here. So for those of you who haven't seen cells for a while, I'm showing you a movie of a cell. This is a cell which is moving, the time is in hours and minutes, and you see the trajectory of the cell. It's so-called the persistent random walk. There are some phases where the cell moves straight, then it switches direction, then it switches direction, then it switches direction. Eventually, it can go back to the original direction. So this is a movie that lasts about a day and a half. If you go into the detail of what the cell does here, you can imagine that, in fact, the cell can be viewed as an ensemble of muscles, stress fibers here, which are ending in focal contact points. So basically, you have the scale bar here, the cell is spread and is applying stress on the surface like this. And eventually, the integration of this stress at low Reynolds number is going to make the cell move, okay? The next point I want to highlight is that this is heavily dynamic. Here you see the point of adhesion, which are all around the cell. And you imagine if I am the cell, I'm pulling everywhere, like this. And eventually, I'm going to get stabilized somewhere, and I will move in one direction. So the first story I'm going to talk about is how do I integrate all the forces that are applied here by the muscle, mini muscle, to have a directed motion in one direction. That would be the story number one. And you recognize the collective effect. It's basically how, when I have an ensemble of focal contact here, am I going to integrate that into a motion? That would be story one. The story 2 and 3, I'll watch the time not to be too long, will be basically around the same question but for tissues. So I'm not going to talk now about a cell, but I'm going to talk about a collection of cells. This is a single cell. This is a neighboring cell. And all of that is going to make a monolayer, which is spanning our intestine, pancreas, you name it, basically. This is what looks like a typical cell layer that is in all organisms. I can repeat exactly what I said before. There is inside each of these cells molecular motors, actin and myosin, that's their name, which are pulling like this everywhere. And if you want to visualize them, this is what it looks like when you play the movie. You see here in red, these are the cell-cell contact, these are point of adhesion, and in green, you see some molecular motors which are pressing like this, which are kind of pulsatile and making the dynamics that you could see here. Everything that I said for the cell motion, I can repeat it here, basically. You have the muscle, which are protein of the muscle, which are applying force, stress, and eventually the distribution of the stress is going to make a change of motion or stress generation. Essentially, the point I'm trying to convey is that with only these elements, you can change shape of cells and tissue the way you want. We and other groups have been proving that. So I'm showing you a typical example. We've been showing that if you prepare a ring of cells, they will undergo a spontaneous rotation. So they will start to rotate in one direction. It is chiral, we can talk about it later on. If you prepare a bit differently the very same cell, you will observe a broken symmetry, returning to Anderson point. If you prepare a disk of cell, they will eventually elongate spontaneously. And for those of you who make liquid crystal, it is entirely detected by the nematic order of the cell inside. I'll show you the movie for that. You see that it breaks symmetry in the direction of the cell elongation. And the third example I want to show you is if you prepare the cell the right way, the same cell, they can undergo pulsation. This is the example that you can see here. Or if you prepare them differently, they can undergo eventually a flow. So what is fascinating is that you have collective effects with the very same cell, and depending on the boundary condition that you have, a disk here breaking its symmetry through nematic order, a ring that is undergoing rotation, pulsation, and flow, you can have any change of state that you would see somehow during development in any organism. Collective effects are back. So basically an ensemble of cells, because of the stress generated by the actomyosin, is going to generate this type of dynamics. So it is around this idea that we keep turning, right? Basically, how do you have a cell dynamic, cell motion? How do you have an ensemble of cells that collectively are going to generate a given shape? So far, so good? It's okay? Okay. So symmetry breaking, I hope I convinced you, symmetry breaking, right? A cell is going to move from one spot to the other one through many focal contacts, or symmetry breaking, elongation, or spontaneous rotation in one direction. So I'm ready to go. There are going to be 3 stories. Story number 1 is going to be collective effect of adhesion point for having a directed cell motion. So that will be story 1. It's echoing the focal contact dynamics I was showing before. The story number 2 is spontaneous rotation as interplay between cell polarity and boundaries. Cell polarity, many of you are familiar with it. And basically boundary conditions are key in the storyline, and this is going to justify the rotation. And the third one, which will be shorter, it's polarity-driven 3-dimensional spontaneous rotation of a cell doublet, is when you take 2 cells, how they undergo spontaneously a rotation. What is the physical mechanism at play? And a teaser for the end, so that you know. We've been proving that the Curie principle that was demonstrated at the end of the 19th century was true also for the cell rotation. That would be at the end. I give the reference also to give credit to all the authors. So the first paper was the first author was Simon Lovecchio. It was a collaboration with Raphaël Voituri and Laurent Navoret. The second story, and with Raghavan Tyagarayan, who also contributed greatly. The second story, these 2 papers were published recently, it was last year, and this is a collaboration with Laurent Navoret, who is an applied mathematician. We had a discussion a moment ago, a difference between a physical theorist and an applied math. I think we can have a long discussion about it. He's a mathematician together with Marcela Chopos. And the third story is a collaboration with Guillaume Salbreux, who is a theoretical physicist in Geneva. And it was the work of Lin Gilou and Tristan Guillaumard and Quentin Van. So I'll be going through these stories, but you see that the spirit will be essentially the same all the time. It's a mixture of cell biology together with physics to capture the collective effect. So I start by the story number 1. And if I boil down the question to minimum, the question that we ask is how a cell is going to move from a point A to a point B. It's simple, right? Why is there going to be a broken symmetry in the motion? So I'm returning to my movie. This is the spontaneous motion of a cell on a flat surface. It changes its shape, it changes direction, eventually it changes direction again. It goes back. There is these processes going on. I haven't rectified the motion yet. To rectify the motion, there is a trick, which is to micro-contact print surfaces. So you take an ink, which is here fibronectin, which is in red, and you print it on the surface. And you come with the cell, and you see how the cell is going to spread on it. This is going to give this. The cell is still active. This is what you observe here. And eventually, if you let the system go with different adhesion ports like this, you can let the cell run. According to you, where is the cell going to go? Yes? Along the line. By symmetry, it's going to go along the line. So basically, you can let the movie run. And you let the movie run, it's going to move to the right, then to the right, then to the left, then to the left, then to the right. Essentially, after 2 days of experiment, the cell has been returning to its original point. You could tell me it's obvious because by symmetry, that's the only way that it can go. It didn't go up or it can go down. The red points are points of adhesion. So the cell is protruding like this, making some adhesion point, and then probing left, right. So it's an active particle, if you wish, but which is adhering as soon as it finds an anchoring point somewhere. Now, if I'm going to a geometry which is a bit more difficult, which is this one, I will again play the game, if you allow me. Basically, you have triangle, triangle, triangle. Where is the cell going to go? Yes. Left. Right, sorry. It will go to the right because... Yes. Anyone votes for the left? No? Right. I would imagine that the most biologists in the audience would say that it goes to the left because the cell here is polarized. So they could argue if you have a polarity here, it would go to the left. So I'll tell you, usually when I give this talk, there are three answers. Either the people are telling me that they go to the right, or they go to the left, or they stay on the same spot. And it's a complex system because here you have a high probability to probe, a low probability to adhere. Here you have a low probability to probe, a high probability to adhere. So you are having opposing probability on the right and on the left. It's okay? High probability to probe, low probability to adhere, low probability to probe, high probability to adhere. So far, so good? So if you let the movie run, basically this is what you observe. The cell is probing to the right, and you see the nucleus that is essentially dancing right and left at low Reynolds number. This is on the right, and eventually it is stuck to the right, and it has been going to the right. So you could say you were right, and you were right, in effect, but it's distributed. Some cells move to the left, other cells move to the right. It's a noisy system, right? And so the idea is that you have a majority of the cell that will be moving essentially to the right. Good, so far so good. To see if the hypothesis was correct, we take another geometry. Here, triangle, rectangle, rectangle. There is a high probability to probe, high probability to adhere, low probability to probe, high probability to adhere. According to you, the cell will go in which direction? To the left, why? More spot to explore and more spot to adhere. So basically, you combine probabilities to the advantage of the cell, so then you will be going to the left. So basically, if you play the movie, it's working fine. So basically, eventually, the cell will be moving to the left, and you were right. There is the tug of war. The cell is fluctuating right, left, right, left, right, left, and eventually is going to get stabilized on the left at the end of the movie. It's a long process. We're talking about 10 hours, 12 hours a day, but eventually you're right, and the majority are going to go in this direction. The last one is a bit boring, but it's basically circle, circle, and I'm passing this one. If you wait more, we ended up showing some time ago a proof of principle that if you let it go, eventually the cell is going to have a directed motion in a long range. So basically, it has been moving to the right, and the point on which I want to insist is that there is no chemical gradient. All right? There is as much, I mean, everything is isotropic here, so the cell has been spontaneously breaking its symmetry and moving to the left. So we call this effect ratchet axis, because if you interact with cancer scientists, usually the dogma is that you need a gradient of molecules for a cell to move directionally. And we and other groups wanted to show that you don't need a chemical gradient for that. What you need to have is the cell to acquire a polarity and then to keep a memory of this polarity. And this is basically what it is showing, that you teach the polarity to the cell, quote unquote. When you teach this polarity, the polarity will be perpetuated over time so that it will continue to move straight. And that was making the proof of principle, existing.
So polarity is not a chemical...
It's not. But basically, we're trying to prove that in addition to the chemical gradient, there is another way to rectify motion, which is essentially what this movie is proving, that somehow there is no chemical gradient right or left. The cell is probing everywhere, and then it is locked in one polarity and then perpetuates its polarity. To give you an insight, for us it was important because there is usually in the community of developmental biology and biology the absolute belief that a gradient is going to cause a directed motion. And in fact, there are many cases where it's not true. In particular, if there is biologists in the audience, you're familiar with the Boyden chamber. If you're a Boyden chamber, you put a gradient of a given molecule, and the cells, in many cases, are not migrating directionally. So chemical gradients is not the full story. It's part of it, but there is another process, which is polarity and memory of polarity. So we are 5 groups who have proven this, and so it somehow means that you don't need chemical gradient to directed motion. Yes?
Although you won't have chemical gradients, but you still have not a perfectly symmetric system. Your cell has a direction, your red spots have directions, and so they can induce direction. I'm saying it's not completely isotropic in that sense.
I totally agree with you. The point here is that what we prove, and this is the next part of the story, is that you have a protrusion which is locally not seeing the full isotropy. So basically, if you wish, the protrusive activity is going to be the key minimal element that will see the docking spot. So there is no, if you wish, gradient whatsoever. It is the protrusion that is sensing locally, and the protrusion typical size is about 200 nanometer. So to go next to the mechanism, we designed with Simon actually, we wanted to have a mechanism, what's going on? Why are we rectifying the motion actually? How come we have a motion that is going to be directional in the long range? This is true in 2D, we and others have been showing it is true in 3D also. Basically, polarity, locking, and memory of polarity seems to be at play. So for this, we made the following exercise. We wanted to increase the bias, we wanted to predict the motion with different topologies, and here we go. We take the triangle, so this symmetry locally, we need to impose a shape to have more probability, and so both locally we have the local probing, and we're going to take the triangle and put the triangle away and away and away. It's like the game, if you wish, on water when you have some stones, you put the stones further and further away. We are doing the same thing, but with macro contact printing. So this is what we do, and eventually we record the motion. So we have the triangle, and we put the motif further and further away, and we see what's happening. So we're ready to go, and we compute the result. So we have the percentage of the cell as a function of the gap distance, which is going like this. To give you an image, 22 micrometer, we have the majority of the cells that are moving to the direction you had predicted, which is eventually to the right-hand side. So it means that we have rectified the motion, and the majority are going in one direction. When Simon came to the lab and said all of the cells are going the same direction, we had a doubt, so he changed the protocol, he turned the camera, he turned the way. Basically, when you have a broken symmetry, you wonder if there is no artifact in the system. There was no artifact, the cells were moving in one direction. Another way to be more rigorous, and we teamed up with Raphaël Voiturier, who is a theoretical physicist in Paris, we computed all the steps. So number of plus steps for a cell minus the number of steps in the opposite direction over the total number of steps. This is the P bias. To be fair with all the trajectories, some cells will move 5 steps, other cells will move 10 steps. We compute this mean polarity, mean bias per step P as a function of gap distance. And you see the function is very nonlinear. When you have the gap distance, 22 micrometer, the cells are moving in the same direction. So we wonder why. Why do we have a nonlinear effect like this? So to do that, we went back to the imaging of the introductory slide I was giving, where you have the focal contact formation. This is the white spot here. So it means that the cell adheres locally, essentially. So you see that they appear very quickly, within 20 seconds. On the left, they're on the right, they appear on the left. This is RICM for the most opticians in the audience. Basically, very quickly, they managed to form these points of adhesion. What we had been showing in the past with others also is basically focal contacts are mechanosensors. Whenever a focal contact makes points of adhesion, locally it will reinforce itself and apply more force. And we showed that the force extension curve of these objects is 2.5 nanonewton per micrometer. For those of you who are not familiar with this unit, this is a typical force that you expect for basically in active matter at the cellular level. This is what you should have. So it means that whenever you have a length of an adhesion point, you can convert it to a force. That's what we did. Now you have the moving, you have the focal contact, the cells from this focal contact, and eventually the points of adhesion and the local stress being applied by the cell is going to be converted into a motion. since we know that focal contacts are local sensor, if you wish, of force, we converted the elongation of the focal contact into force. This is the cell, time t0, time t2, time t3. This is the conversion of the elongation into a force. You add up the force, and we are at low Reynolds number, meaning that the force should be equal to 0. Basically. There is no acceleration, as we saw in the lecture on Monday. So time t0, time t2, time t3, we converted the point of adhesion into a global force, and now I can give you the amplitude of this force, which is the last slide here. Nothing on the y-axis is coming up, but on the x-axis, you see that there is increase on the force. We go from 40 nanonewton up to 130 nanonewton during the motion, and then it goes back here. So it means that somehow, by integrating the force, I can end up with, potentially here, an estimate of the friction. What is the friction? The friction is force equal alpha v. Force is the force applied, v is the velocity, alpha is the prefactor. So if you know the velocity of the cell, and if you know the force, you can end up with the friction, which is this one, 25 Newton second per meter, and it gives the value that is expected for a cell that was demonstrated. So far, so good. We are on the right track. I'm summarizing where I stand. The cells are applying force everywhere, and eventually, if there is a broken symmetry, there will be more force, and the cell will be moving in one direction. Now, if we are naive, we should imagine that the cell here is probing on the left, here it's probing on the right, and the intercept between the point of adhesion on the right and on the left should predict the nonlinear response I was showing before. This is very naive, because I remind you that the mean P that we were obtaining as a function of gap distance was very nonlinear. So we were fully wrong. This type of estimate was naive and very wrong. And we wondered where was our error. So with Raphaël Voiturier, we came back to measurement, and with Simon Lovecchio. And basically what we showed is that the number of focal contact that you see here, you know, the points of adhesion with the surface, when we plot this number as a function of area that we offer to the cell, they increase and then they saturate. So if you wish, there is a point at which you cannot make more point of adhesion on the right and on the left, and then there is a plateau, and that's it. You cannot have more, which we had neglected before. So then we came back to our estimate, and with Raphaël Voiturier, we ended up writing the P factor as a function of tangent hyperbolic, which is the proper functional dependency to capture a saturation. So this is what is depicted here. Tangent hyperbolic A plus over A0, which is the area on the plus side, and the tangent hyperbolic A minus over A0 over the sum, and now you end up with a nice fit. A physicist is happy when he has a nice fit, basically. That's somehow a relief. It means that things are, you know, more or less under control, and so far so good. Good, but
this choice of tan hyperbolic is purely empirical, I guess?
Empirical. It's empirical. Basically, you have a saturation, so tangent hyperbolic should be the natural one. And then comes the story of the referee number 3 that many of you know. Number 1 is happy, number 2 is okay, happy but, and the number 3 doesn't form the paper, right? So the referee number 3 was arguing, okay, fine, you have a nice fit, but a good physicist should be able to predict a new configuration and should test experimentally the configuration, because that's how physics works, right? You have a quantitative model, you predict it, then you test. If you don't have it, the paper is rejected. Well, so we went back to the lab and we said, let's try, right? So we wanted to have a rectification in exactly the opposite direction to make the point and to convince referee 3. We don't know who that is. He didn't reveal his identity, so I can speak freely about the person. So basically, it was a fair comment. There was no fitting, the only fitting point was the area that was needed for the saturation. So we went back to the experiment and we designed teardrop. So teardrop has this motif that you see here. And basically what we showed is the interdistance between subsequent teardrops. So we have a teardrop and the neighboring teardrop on the neighboring. And Simon repeated all the experiments. Basically here, there is the nonlinear behavior for the triangle. And then what he saw what we showed for the different teardrop as a function of gap distance is that we had the rectification exactly at the spot that was predicted by the theory. So basically, by changing the triangle into the teardrop, repeating the experiment, we had the prediction that was predictive. To convince the referee 3, we plotted the experimental mean P as a function of the theoretical P, and you see that they match. So basically, we can predict any motion whatsoever that we want. So far, so good. The paper was accepted, but I'm coming back to the original title that I was giving to this talk. We had a collective effect. Where is the collective effect? The saturation that I was mentioning to you before means that an ensemble of focal contacts, 8 or 10 focal contacts, is a new scale that needs to be considered. So somehow, I have 8 to 10 collective focal contacts that are acting in concert on the right and on the left. If one of the sides is outcompeting by this 8 to 10 focal contact, it wins, the cell polarizes and keep its polarity. So somehow it means that you need to consider a new scale, which is the typical area, which is 10-ish focal contact, which as a whole is behaving in a new way, which is going to direct what the cell will do. Okay? So that's the end of story 1. But you see the spirit somehow. It's trying to break the symmetry, and by broken symmetry, try to understand what is the individual unit that as a whole behave differently.
You're saying it's the saturation which is the emergent behavior.
That's right. Yeah.
So there are a smaller number of
Focal contact. You need a new entity. To return to the herd image, if you wish, it means that if each focal contact is a sheep, you need 10 sheep, which as a whole is going to be the new entity. So basically, 10 on the right, 10 on the left, they compete, and eventually one win, and when one win, the cell gets polarized and then continue its motion. So it's, returning to Anderson, it's a way of saying that you cannot predict that if you don't do the experiment. It's impossible, basically. You can say something on 1, but you cannot say something on 10. You need to run the experiment to decipher this new scale. Yes?
Once a cell develops this polarity,
Yeah.
to what extent will it maintain this polarity? Does it depend on how far the cell is going, or till it reaches the next point where it cannot do it?
That's an excellent question. So the noise is continuously on, basically. It's an active fluctuation with a spectrum of fluctuation. So it's not like whenever the polarity is locked, the cell is going to be moving straight. As you could see in the movie I was showing to you before, there is some stochasticity in it. On average, it will always go to the right direction, but noise will be always potential. If you a way to see that, it's you can introduce a diffusion in the polarity, which will allow the system to probe in another direction. But in effect, at the end of the day, the cell will move in the right direction. You see in this type of reasoning, there is at the same time deterministic behavior associated with noise, which is making the system also going back and forth. So I'm moving to story number 2, which is a spontaneous rotation in epithelium. So I was teaching this in the master that we have in Strasbourg for biological physics, and it is the paper by Turing, and it's really the way it happens. Probably many of you know Turing, first of all, I'm sure, but on top of that, the fact that the mathematician Turing was also interested into biological physics, and he made a key contribution that keeps being quoted. The paper is the chemical basis of morphogenesis. He was a mathematician, and he wrote, the reaction, diffusion reaction, Belousov-Zabotinsky oscillating reaction that came from his seminal paper, actually. And what he writes in his paper, he says, the reaction diffusion are considered in some detail in the case of an isolectic ring of cell, and I like the next sentence, a mathematically convenient, though biologically unusual system. Indeed, the ring of cell, well, it's not obvious to find this in nature, but he said, as a mathematician, it has the merit to be symmetric, so let's consider that. Well, we said, what about trying? So this was only the source of inspiration, the rest is not Turing pattern at all. So we macrocontact preach ring, and then we are ready to go with the ring of cells. You have the same glue as the story number 1. It's fibronectin, for those of you who are biologists, and you put the cell, and then you have a ring of cells. These are now epithelial cells. These are the tissue I was presenting in the introduction. Comes the next slide, which I hope will be visually already understandable. You have a large ring, an intermediate ring, a smaller ring. The 3 sides, this is the same scale. And I'll just let the movie run to give you a sense of what we are trying to show. Again, collective effect. So you see the time is in hours and minutes, and you see fingers going. If you look carefully, you see that somehow there seems to be a coherent length at some point. You have a kind of trains of cells which are eventually colliding, and eventually you have a finger appearing. But there is a dynamics which is puzzling, but still no rotation. We decrease the size of the ring. There is not rotation yet. It's a very different dynamics. And then we decrease again the size of the ring, and we start seeing something. There is a beginning of something that seems to be a rotation. We haven't changed anything but the diameter of the ring. So it's funny, right? There seems to be a spontaneous symmetry and the broken symmetry in effect because one sense of direction is privileged compared to the other, and we haven't changed anything else than size. So we wondered why and how. We went to PIV. Basically, back on the envelope is a way to track the velocity and to have correlation between velocities. And this is depicted here. And if you plot basically the correlation function of tangent velocity for all the diameter, 1 millimeter, 300 micrometer, 180 micrometer, it gives this respective curve here. If you take the tangent to the origin, you end up with the correlation length. Back on the envelope is how many cells do I need to have a coherence? It's the train and the Huygens metaphor somehow. How many cells do I have to form a new entity like the focal contact in story 1? So it's 330 micrometer. To give you an AD is about 10 cells. We are coming back to this number of 10 cells. So 10 cells from a new entity. It's the emergent object that now I'm going to consider. If you think about it, this is trivial. If I have a train of 10 cells, if I put a perimeter that is equal to the length of the train, it will rotate because somehow it's a coherent length, so it will undergo a rotation. So we try this. Yes, there is point. What do you say? It's a coherent length. So basically what we did next is to go exactly to the diameter of the coherent length, and now that you see, it's rotating. So basically we are exactly at the coherent length, and now you have the rotation that is undergoing, And if you plot the parameter that is the coherent length over the perimeter, it's probably correlated for the large ring, a little bit better intermediate, smaller ring a little bit better, and if you come to 80 micrometer, all the rings are rotating. So basically now you have a sustained rotation. Comes the point, which is usually a problem or a question that I have in this type of presentation, is that the majority are clockwise. And the question is why? And my answer is I don't know. Basically, we can have a long conversation on this. There is a broken symmetry. Most of the groups working on rotation have seen chiral rotation, which seems, and it's a question I had earlier this week, which can be correlated to the broken symmetry of the body axis, actually. That at some moment, our heart is on the left. There are some people who have the heart on the right, and everything is fine. So basically, the majority of people have the heart on the left, as a matter of fact. So the broken symmetry in early stages of embryogenesis seems to be tightly related to broken symmetry of that type. But again, the rest is a lot of philosophy and epistemology, fascinating, but I don't understand this result somehow. But it is chiral, definitely, like many people see that. So we wondered yet how the rotation was operating. So for this, we tracked the onset of rotation as a function of time. Cleverly, Simon, when he made the experiment, was having all type of time scale for the rotation. Sometimes he needed to wait 1 hour, sometimes 5, sometimes 10, sometimes more. And basically, he decided to have all the time scale at the same time. So it's a pseudo time. Rotation starts here, and before that is the onset of rotation. Why was he doing this? He was doing this to show that basically there is a time scale which is extremely fast. Coherence is a fast nonlinear process which takes time about an hour. So the cells do not rotate, and then poof, they start undergoing a rotation. So it's a pretty fast process. We wonder why. How does it emerge? There is a trick in cell biology, is that you can label cell fluorescently inside of the cell. And if you label them, you can follow their polarity. So you have a cell, all of the cells are connected with each other. Some cells are polarized this way, some cells are polarized the other way. So somehow there is a competition between polarity. If a cell is polarized, usually its velocity will be in the same direction. If it's polarized like this, its velocity will be in the same direction. So they kind of oppose direction. One is going to go this way, the other one is going to go the other way. So this is what we computed, and you see the movie here. A cell is fluorescent, inside it starts rotating. And the punchline is that you have two polarities, polarity clockwise, polarity counterclockwise. Since everything is coherent and adhesive to everything, again, it's a tug of war between right and left. If you have a tug of war, you don't rotate, basically. Some cells are going to pull clockwise, other cells are going to pull counterclockwise. We made the same experiment with another protein, tight junction protein. I'm going to show you what it looks like. It's the top of the cell layer. Basically, what you see is that essentially you have a stretch. The cells seem to be pulling on each other, and this can be quantified. This is what Simon did. I cut the long story short. What you have is that there is an increase in the stress before the rotation, and at the rotation, the stretch decreases, as if the cells started to relax. So you take my first point, you take my second point, and you come with a potential solution. The cells have opposite polarity. The time it takes for them to resolve their polarity, meaning switching all the polarities so that they're all in the same direction, is the time needed for the coherence to start. If this hypothesis is correct, the time needed to reach coherence should be dependent on the fraction of the cell with the same polarity at time t0. To check that, what Simon plotted was the time of coherence onset as a function of percent of aligned cell. If the percentage of aligned cell is 70%, the time of coherence is reached within 50 minutes. If it is lesser, the time of coherence is larger. It's very intuitive somehow. You have opposite polarities. Polarity is going in this direction, the other one is going in the opposite direction. If they resolve themselves, it will take more time if you have more cells to resolve. When all of them will be resolved, eventually they will rotate in the same direction. So far, so good. As I was trying to convey this morning, actually, there is another problem, is why do the cells are organized in this manner? Maybe I will go very quickly on this one. The cell self-assembles its own prison here with actomyosin boundary. And if you want to understand what's going on, you can see here a cell that is labeled also here, which is having its own actomyosin bubble, which is preventing to go away. So the cell is going to orient essentially because it's building its own boundary. I'm going to pass this just to go to the numerical simulation, which I think in the context of the talk today will be the most relevant. And again, returning to Vicek, who was mentioning during one of the actually sessions. We teamed up with Laurent Navoret, that I was introducing before, and with Marcela Chopos. It's not because you have an intuition that it is correct, that by the same token it's correct. You need to run the simulation to be absolutely sure. And what Laurent and Marcela designed was a Vicek model. Basically, in a Vicek model, you take each cell as a particle, you take a polarity for the particle, you take a velocity for the particle, and as I mentioned very quickly before, there is a boundary which is set by the actomyosin. This is the ingredient. And then you set some rules of interaction. So this is a mathematician writing. I will drive you through this equation of polarity. There are two more equations which are needed to solve the problem. This is the variation as a function of time of the polarity of the particle K. The first term is a relation on the mean velocity direction. Basically, the polarity is going to align with the mean velocity direction. The second term is going to be connected to the relaxation on the mean neighboring polarity. On average, all the cells have a given polarity. The third term is connected to the force of the cable that is outside or the cable that is inside. And the last term is the diffusion term of the polarity. A polarity can a bit rotate in different directions. The pre-factor here can be measured experimentally, which is the table that is here. And then you run a simulation. It's work. It's hard work, actually. And that's what Laurent did. This is the particle simulation exactly mimicking the set of equations I was showing to you before. And you see that if you wait sufficiently, the system is going to undergo a spontaneous rotation. And now it starts rotating. So somehow, once you have this with a calibrated system, you start thinking that the system is correctly described. This is what's happening experimentally. So far, so good. It seems to be like mimicking what we hope for. The next step was the way of saying that, okay, is it good for one, but it is good for all the other situations? You know, the reference 3 of story number 1 is coming back here, but we anticipated it. This is depicted here. With Laurent, we had calibrated what was happening here, and then when we went up to the larger diameter of the ring, we ended up with the right shape. You see here, the shape is similar, and it's not only a qualitative comparison, it's working also for the index of coherence that I was showing to you before in the introduction. This is the experiment and simulation, experiment and simulation, experiment and simulation. It's fitting pretty well. So it means that we were okay, basically. It means that somehow, based on the understanding of the tug of war, we could return to the more general property quantitatively. I'm summarizing where I stand, and I won't be known for the story number 3. In this story, I was just saying that collectively, the cells, because they adhere to each other, and because there is a tug of war between polarity, eventually, when they resolve their polarity, they will all shift to the same polarity and eventually start undergoing a rotation as long as the perimeter is equal to the length. You're back to collective effect. It means that a collection of cells can undergo a spontaneous rotation. It's not only a physicist game, because if you return to, and I will go back to that close to my conclusion just in 5 minutes, rotation is many places in biology. It is present in spheroid, it is present during development. This kind of coherent length seems to be present in many places. And another suggestion that we make is that this new length could determine the length of organ or the length of natural morphogenetic events. It will be a physical length somehow, which is associated to biological phenomena, biological network, but also it would be a length that would set dimensions inside the growing body. 5 more minutes? So the last story is about rotation in 3D, and I will make it very short. We are now in 3D. We put 2 cells in 3 dimensions inside the matrix gel, which is a matrix. I think the image speaks by itself. It rotates, right? I mean, this experiment has the merit is that you put the sample, it works, but whenever you put the sample, it rotates. So far, so good. Another rotation, great. How does it work? Well, it's rotating. You see also that there is a yin-yang shape at the interface. It's going to be undulated. But all of them rotate. So we wondered why it was rotating and how it was rotating. So here there is no chirality, because you have 2 cells interacting far from surfaces. So by symmetry, you cannot name a chirality. It's a chirality, you need the surface for that. So basically, chirality is irrelevant in this storyline. But we wanted to show what was the stress generation. I won't go through the detail of this experiment. I will show you with my hand somehow. You have 2 polarities which are like this, with myosin. I should not do that for the noise, but basically you have 2 polarities like this in each of the cell. Stress generation with myosin spots here, stress generation with myosin spots here, and the system is doing this. Basically, you have 2 polarities which are changing each other, which eventually is going to yield a direction like this. This is the result of this series of experiments that I'm going to cut short to make them more going to the conclusion. Basically, what you see is that you have some spots of myosin that you see here, which is depicted on the left and on the right. If you want to have a movie of what's going on here, you have the myosin, you have the cadherin, which is cell-cell junction, and you have the F actin. Basically, you see the 2 interfaces which are essentially doing this type of dynamics. So far, so good. We tried to make sense with quantification of what was going on in this rotation. So for this, we first look at the motor. We prevented the motor to act, which is a drug which is preventing the stress generated. You see that the interface becomes flat. Then we try to laser ablate the point of application of stress. You see that the rotation stopped and recapitulated rotation with the appearance of the stress generator. Third experiment, and I'm going super quick for an experiment that required more time actually to set up. We created locally some hotspots. So you have here the stress generator, By optogenetics, we applied an extra spot, and we transformed the rotation into a translation. Stated in two terms, two words, when we suppress the stress generation, we stop the rotation and the interface becomes flat. So we touch the right button, set it in, and it is reversible. Okay? Now we wanted to relate rotation, interface shape, and myosin activity, basically. Are they all connected? So for this, we quantified, segmented all the cells. We quantified their rotation, it's half a turn per hour, and then we make the circle of quantification of the interface. The interface can be decomposed into 4 modes of decomposition of shape: saddle node, ball, threefold, and yin-yang shape. We saw that when we observed all the interfaces, the 4 modes were existing. So we had 4 modes present in our system. So far, so good. For the myosin polarity, we defined the polarity I was doing with my hand. You have here the myosin spot. We could define the polarity P1 for one cell, polarity P2 for the other cell. So far, so good. And the third one was now we are ready to make the circle between all the parameters. So we wanted to relate, whenever you have a spot like this, can you relate the polarity with the sense of rotation? The answer is yes, because when the polarity is like this, the rotation will be like that, which is the correlation plot that is here. Because considering the other way around, when we compute the interface shape mode, which is like this, we could predict what would be the sense of rotation. And third, when we computed the polarity, we could compute what the interface was. So basically it means that we have a consistent, there is no mic, but somewhere. Can you hear me? I will shout. I don't know. Can you hear me if I shout? Yes? And I will stop anyhow. Yes. So basically what we did then is to Guillaume Salbreau and Quentin Vagne, they run the simulation, numerical simulation with the active gel equation, which is depicted here. And you see the rotation occurring here together with the interface shape that is a yin-yang shape. So basically it means that the proper theory associated to it was capable of recapitulating what we observe, and he also managed to mimic the rotation together with the translation I was showing to you before. Very last slide and then summary. Everything was fine, but as I mentioned before, the different modes here were present experimentally. We only had one, actually, that was present in the theory. So we were lacking something. And we return to the Curie principle I was introducing in the introduction. It's a principle that says the symmetry of the causes are to be found in the effect. You are probably familiar with this principle. And Quentin Vagne and Guillaume Salbreau, they took essentially the stress generation and their symmetry. They took essentially the compatibility with the interface shape. And basically, this stress generation was compatible with this mode, that one with this mode, that one with this mode. And when all of them were integrated, they could recapitulate this type of distribution of mode. But the only one that was consistent with the rotation was the yin-yang. So basically, that was the only way that we could have a rotation, was essentially the yin-yang intershape. The other one could not be, proving that somehow the symmetries of the cause are to be found in the effects was also tested in our experimental system, and to our knowledge, it was the first time it was tested for cells. So as I was trying to say before, this rotation that we observe in 2D and in 3D, they are ubiquitous. I'm showing you here a rotation of cyst in 3 dimensions, a rotation of pancreatic spheroids cultured in vitro. I'm showing you next a rotation in the follicle of the developing Drosophila. I'm showing you next a rotation actually in the dynamics of human mammary glands that you can see here. Everyone is seeing rotation at the moment in vitro and in vivo. So it seems to be a built-in property of the system in vitro and in vivo. So it goes beyond, if you wish, collective effect. It seems to be happening really during development. So if I'm summarizing story 2 and story 3, story 3 here was about rotation. explained by two polarities changing each other, provoking an interface that is going to buckle consistently with the Curie principle, and leading to the rotation I was mentioning to you before, and properly tested numerically by the active gel theory. And the story number 2 was about spontaneous rotation on 2D flat surface, tested by a Vic-check model with rule of interaction between particles leading to the rotation. The two stories are tug of war story. Tug of war in 3D or tug of war in 2D flat, and the coherence leading as a result of the resolution of these different polarities. So basically, the three stories have the same spirit, as I was trying to say. The story number 1 was about ensemble of focal contact behavior leading to an emergent behavior of 10 focal contacts competing leading to direction. The story number 2 and 3 were about the same spirit, but basically you got my point. It goes beyond the molecular description or the single object description. So more is different is the key message I was trying to convey, and this is the slide for acknowledgement. So the story number 1 was led by Sylvain Mauvecchio, as I said, in close collaboration with Laurent Navoret and Marcella Sopos and essentially Raphaël Voiturier. And story 2 was again Simon Lovecchio, but this time with Laurent Navoret and Marcella Sopos. And story number 3 was Lin Gilou, Tristan Guillaumard, in very close collaboration with Quentin Venn and Guillaume Salbreux. And I thank you very much for your attention.
The patients that we showed in the in vivo cells, they are of both kinds or only one kind?
So, to my knowledge, but I need to be very cautious in what I'm going to say, most of the systems which are reported in vitro and in vivo are chiral. Chiral. So we come back to the point of the origin of its chirality and the function of its chirality. The natural one that I've been hearing from many groups is broken symmetry with, left-right. Many symmetry are broken in our organs, and you need an origin for that. And such a mechanism of chirality will be a key one, because you have a long range, it can be robust, it can be reproducible, there can be some accidents. That was the example of the heart, which I was mentioning before. But most of the...
different scale than cells.
What do you say?
The body is different scale than the cells.
Yes, but two things. One is that during embryogenesis, the broken symmetry events come very early. So basically, the point is the onset. And then you perpetuate what you've been creating. So the argument is that we all started by a single cell. I mean, I'm saying something trivial, but we all started by a single cell. And whenever the cell proliferates, we have a ball of cell, then we have a lumen inside, and then some cells are going to change their state. And eventually, locally, you will have a local entity. If you have a broken symmetry at this stage, it will continue. So it is the transition that is important. So that's why it's becoming more and more a trendy hypothesis, which seems to have some basis somehow. That it's a, and another way I want to say is that the advantage of this mechanism somehow is that it gives long range. It spans 5, 10, 20, 100 cells. Whereas, it can be very robust if you prove it. You see what my point is that, yeah. And it's true for C. elegans, apparently, quite documented, which is a worm, and it's becoming more and more documented.
Students,
the second problem.
Yes.
The side at which the circle starts rotating, does it depend on the individual organism size? Like for different bacteria, that size will be different and will be dependent. And will that connect that the independent size governs when the symmetry will be broken, right?
So I like your question very much. My answer will be yes and no. Okay. So the part that is yes is that in biology you can, as you know, you can manipulate the cells. So if we make the cells overexpressing cadherin, which is a protein of adhesion between the cells, the persistent length is larger. Coherent length is larger. So somehow there is an experimental way to tune the system so that the length is larger. You could tell me it's very intuitive. If I have a, two monomer, if I take chemistry as an example, and if I increase the bond between the two monomer, I'm expecting the persistent length of this polymer to be larger. You are more sticky. If you are more sticky, your length will be larger, which was not your question. Your question was size, and I know that. So that's why I'm saying it's yes, because you have a way to tune the cell-cell interaction. And this is the second part, which is known. It's not necessarily the cell size which is the key element. It's rather the coherence of the cell. So you can have a smaller cell size, but if you have a larger coherence, you end up with a cell size, a length of coherence that is not the same, but with larger number of events. You see what I'm trying to say? If you want to have an analogy for persistent length, I think it's the best one. A persistent length in polymer physics is a given, right? It can have n monomer, 10 n monomer. It depends on the interaction between the individual monomer. It's about the same here. It is the persistent length that should be the key factor.
I'm sorry, my biology is very poor, but if I remember, cells make up tissues.
Yes.
Now, here when you see this emergent behavior, there is a length associated with it. So if you have 10 or so cells, then this normal behavior starts to show. Is this coherent length in some sense the onset of tissues?
Yes, yes. This is exactly what I wanted to convey. Exactly.
This is the threshold beyond which you would say that the cells have accumulated to form a tissue.
That's right.
Something like that.
Exactly. It's exactly this. And if you wish, it is typically a place where you need collective effect because you cannot predict from the individual cell behavior. It's exactly the point, is that the ambition or the claim, or I don't know which expression to use, is the way of saying that this is the mechanism. I mean, we don't say that the one that I show here, but basically an extrapolation of this principle should be applied for any organs, because how else could you do? I mean, it's exactly. Yeah.
So you gave an analogy of herd.
Yes, it's exactly a herd. Yes.
Just imagine that if there are 2-3 animals which are crazy
Yes.
entering the herd,
Yes.
they will disturb everything.
Yes.
So like that, cells also can have some bad cells coming in.
Yeah.
And then how will that
Yes.
pattern?
So I take your metaphor literally. Whenever you have a cell in cancer, which is going EMT transition, which is epithelial to mesenchymal transition, basically you have a coherent layer of cell, and one cell is separating from this neighbor to become a single cell. It is a crazy sheep, right? So you have the cell that is going away. It's becoming alone. So there are 1, 2, or 3 that are going alone. It is specifically a typical explanation for cancer onset, where few cells are going away and they start getting polarized and going in the direction that should have never gone to. Then they go to the blood vessel, they navigate somewhere in the blood vessel, they dock in another organ, they enter the organ, and they start proliferating, which is metastasis. So you can continue the metaphor all the way through.
So in case of aggressive cell division,
Yes.
which is cancer cell, you may have different behavior. Or
Absolutely.
patterns.
Absolutely. There are two answers for that. I would say that obviously yes, because then you destroy a local order that was present. And there is the other argument that I did not present too long because I didn't want to go into this, but in the rotation I was showing to you, when a cell divides, it has 2 opposite polarity. So if you had a coherence rotation, when a cell is going to divide, it's going to stop the rotation because now you create a polarity in the wrong direction. Imagine if you have overproliferation of cells. If you had a coherent motion that was indispensable, if cells proliferate everywhere, you will arrest the rotation, which is another way to answer your point. Is the way of saying that crazy cell, basically, either they will go individual cell going somewhere, or you will stop a continuous motion that was at play. But when cells divide, they have opposite polarity, so they are, polarity breaker essentially.
Sir, in the rotation system, cells are confined initially in a circle.
Yes.
And then because I think this movie is about 24 hours or something.
Yes.
So cells must be dividing also at the same
That's right.
time. And then why were the cells not going outside the periphery? Why
That's-
is the tendency to go just inside and filling
Yes.
the circle?
That was, I was going quick on this one. I said that the cells were building their own prison. I don't know if you remember I was talking about. So basically the cells spontaneously are building a supracellular cable that is preventing them from going away. It's a supracellular assembly that you find all over the place in vivo, which is the cell fixing its own boundary. So basically, it is the cell that is generating this boundary spontaneously that is blocking it. So basically, even though it would try, it cannot because it has its own limitation. So it's a spontaneously formed actomyosin boundary. And your question is very fair, but the cell does it by itself. We don't have to do it. It does it. You see the point? I mean, it's a cable. And for the simulation, basically, we needed to add active forces in the process to recapitulate the rotation. Without active forces, no coherence.
What type of simulation it is?
I'm sorry?
What type of simulation it is?
So it's Vic-Check model. The main rules are the ones set by the equation I was showing to you before. So it was a rule between alignment between polarity and mean velocity and polarity alignment plus diffusion of polarity. And basically, in the phase diagram, you play on the prefactor, and the prefactor, we determine them experimentally. That was the table I was showing. You know, it was a simulation of the rotating particle. And for a small size, it was undergoing rotation. When we were increasing, that was what I was showing before.
So, if there are more questions, one
Sir,
last.
has it happened that you labeled only a single cell in that circle and
Yes, yes.
So it is also taking this.
Yes, so if you have a single cell in all, you can have its polarity.
I mean, one colored sheep among the herd.
Well, that's right. I have one red sheep. I have one blue sheep in the middle of all the other sheep, and that allows me to focus on the one that I want. That allows me to know its velocity, to know its polarity, and if you wish, it allows me to say, in this collective effect, how this single object is behaving. Exactly. And this you can do with biology. So basically, for the collective effect, it's ideal, because you can track every single object, and then you make the measurement, and so on.
Okay, let us conclude and thank you.
Thank you.